So welcome to today's off-day workshop on PIANC Fender Guidelines 2024 by Working Group 211. I would say this is an extension to last year's session that PIANC has organized at Jacob's office, going through the insights of the new Fender Guidelines. This would be like a full-on workshop with focus on specific modules such as design, risk management, and we have the presenters from the Port Authority and also the manufacturers, Fender manufacturers here. So once again, I welcome you all for this off-day workshop. Let's start with the acknowledgement of the country. PIANC AUNZ acknowledges the traditional custodians of country throughout Australia, including the land on which we gather and meet today, and recognizes their continuing connection to land, waters, and community. We pay our respects to them, their cultures, and to elders past, present, and emerging. Before I move on to the program, just the housekeeping rules. We have the toilets on the right side of this auditorium. I think male is closer to this and female is just the next hallway. And in the event of highly unlikely of any fire incidents, we just follow the instructions from Engineers Australia staff. Then I also request the attendees to either switch off their mobiles or put on silent mode to have a smooth conduct of the presentation. So we have completed the registration, and I'll start with the introduction of the PIANC and the activities and events that the PIANC conducts and contributes to the maritime industry. Then we have 4 sessions included in this workshop, starting with a design focus module by Harvinder Singh, followed by the risk management by, again, Harvinder. Then by Sam on asset owner focus. And then with a tea break, we have Trelleborg here that they can run through from their perspective, manufacturer's lens. And towards the end of the workshop, we have also the panel discussion. My apologies. Here we have Sam and James also. It's a last minute change. I couldn't update this. Then followed by our networking session. Can I ask Sam to talk about what PIANC is and the activities?
Thank you, Harry. Oh, good afternoon. Good to see you guys here. A lot of familiar faces, colleagues, and old fellows that I'm seeing here. So this is what I used to present. This is regarding the PIANC, and probably you have seen it, but this is my way of presenting PIANC, and I try to put it in one slide as a nutshell and put some just focal points from the time. So you have seen it. PIANC has been established in 1885 as first navigational congress in Brussels, and the name is Permanent International Navigation Congress, and that's the reason the acronym is coming from that. But then they started to change it to International Waterborne Transport Infrastructure. So they still kept the logo and the acronym as it was from the beginning. So if we get to the history, in 1869, the opening of the Suez Canal and building of the Cutty's Ark, that was the time, and I believe that was the latest Cutty type vessel being built. And then we have in 1885, almost more than 16 years later, we have that Navigational Congress in Brussels, and that was established by ship owners because they wanted to, establish some guidelines and make everything consistent across the world and enhance the transportation effectiveness. And then you will see in 1902, the formal establishment of PIANC happened, which, this is what we are seeing. They just focus on developing guidelines, and they are still doing that, after 100, probably 50 years in the industry. In 1914, we have the opening of Panama Canal. You have seen the story. The French started, they got issues in terms of the budget and, sickness of the labor. And then just they paused the construction, and the US guys, they, came back and they finished the canal. That was the, one of the monuments in maritime transportation. And then in 1950s, that's my, assessment, the change of the good transportation, and that was the introduction of the container ship. That was the first time we started changing the transportation, and the container ship revolution happened in the sea transportation. And now you have seen the up to 24,000 TEU container ship in the market. We don't have it in Australia, but if you go to the China, Shanghai, or Singapore, you will see the ports that accommodate such a large ship. For your information, that ship length is around 350, 400 meter LOA, and the breadth going to be around 40. So that's a massive vessel size. I was asked that question: are we going to have a larger vessel, more than 24,000 TEU? Probably no. And the reason is that in terms of the structural stability, we are not able to develop larger vessels, larger than what we already have, and also economically is not feasible to have that unless new technologies arise in the future. So then in 2000, 2010, the number in 21st century, the size and number of cruise and container vessels increased significantly. And they when you increase that one, the port needs to accommodate. So that was the time that, the Port Authority and investor, they decided to enhance the infrastructure. And in 2002, that was the first navigational congress held in Australia. So that was the first time in Australia we recognized PIANC, and we started to develop the national section. Within almost 2-3 years, we are one of the biggest national section of the PIANC. And our contribution to the working group, it's pretty significant and visible. And in 2024, we are in the era of technological advancement, climate change, and also the impact on the coastal and maritime infrastructure. I will pass that one. This is the chapter. So Queensland is one of the regional chapter of the PIANC, and this is, the leadership committee members. Some of the members you probably can see in the audience. And this is, our, end year, it was last year, 2024. This is the chapter events we organized in 2024, starting with the Queensland Government Hydro Lab Technical Talk and hydrogen, design of the breakwaters, and even in terms of the Fender, Harvinder just, offered, his kindly presentation last year, and that was a quick 1 hour, 2 hour seminar, and that was the initiation of, the need for that workshop. So we are working since, last year in order to make that, workshop happen. Offshore wind seminar, I guess that was the first seminar we organized it here. We didn't see much appetite from the industry and from the government in Queensland. Probably in Victoria and New South Wales, there are more, appetite to develop offshore wind. So we didn't continue with that one. We used to go to the regional area every year. Gladstone was the last year technical seminar and port tour. It was almost a day, event there. It was pretty, successful. And then, as I mentioned, the final, the end year celebration and discussion. this is what we planned for this year. And this is what we are here navigating through new Fender guidelines. And then in August is a coast and port. This is the collaboration with Engineering Australia 50-50. We do it every 2 years. And then in October, we are going to have one major event in Darwin. And then we have YP leadership breakfast. This is what we do. We try to outreach to the students and young professionals, because these are the future of the PIANC and our commitment to the worldwide working group. I guess that's all. That's just enough. Thank you very much.
Yeah, thank you, Sam. I did not want to introduce him second time because Sam is one of the presenters in this session. So Sam is our chair for PIANC Australia, New Zealand, Northern Chapter. And I thought of introducing myself at the time you were showing the photograph for the PIANC AUNZ leadership team. So I'm Hari Panchmurthy, one of the members of PIANC AUNZ. I'm also a principal maritime engineer at Jacobs. So let's have our session one. I think we are going on time. Session one and also two is being presented by Harvinder Singh. Harvinder Singh is a principal engineer at Jacobs with over 20 years of experience in ports and maritime infrastructure. Harvinder represented PIANC AUNZ on the PIANC Markham Working Group 211, contributing to key sections of the report, including design, testing, and manufacturing of marine fender systems. He is a fellow of Engineers Australia and a board member of PIANC AUNZ. He is known for his innovative approach and commitment to advancing engineering standards in the maritime sector. He is also passionate about leveraging innovation to solve complex challenges in our industry and continue to be a driving force in shaping the future of maritime infrastructure. So the two sessions going to be offering us a clear and practical guidance on the design, assessment, and risk management of fender systems, addressing both current challenges and emerging opportunities in the maritime sector. Developed through global collaboration and expert consensus, the WG211 report represents a comprehensive and forward-looking framework. While it began as an update to the 2002 WG33 guidelines, the final document is a complete overall and now stands as a new standalone guideline, fully superseding its previous version of the report, WG33. May I now call upon Harvinder Singh to present these two sessions for us. I'll have to put my, isn't it? I'll put my your presentation, session one. Just bear with me. Session one. I have down. You see? I'm sure, yeah.
Like every event, there's always a technical glitch. Just give us some time.
Saved outside. Yeah. Yeah. We can go.
Yeah. All right. Thanks a lot, Hari. Thanks all for taking the afternoon to come and attend this event. I really appreciate your time, and I'll try to make it as valuable as possible and provide you all the insights about Working Group 211. Now, how do you move this forward? This one here. Let's hurry. I'm struggling to move my slide forward, so I need some technical help with this. How do you move this forward? Okay. I think the computer seems to have frozen. Just got to get Hari back on this. It left me a bit of a problem.
Oh, yeah. Try with that.
Yeah.
This middle one.
Yep,
Yeah.
it's working now. Thanks a lot. All right. I thought I'll quickly give you a bit of an overview of what today's session is going to be. Now, I'm going to do two modules. First module is mainly for a design-focused model. So it's probably going to be more applicable for designers who come up with concepts, who develop a system design before it goes down the path of being constructed on site. And the second module, I'm going to focus more on an asset owner perspective. So there's a lot of information that has been packed into Working Group 211 that applies for asset owners as well. I think that's something which I'd like to develop more into the second session. Now, my program today is going to be more along the lines of introducing 211, and then I've taken out the slides for principle of fendering. I think that's quite basic. A lot of us here are aware what a fender is, and we are aware of how to design one. We've done one before, but then I'll get into berthing energies, partial safety factors. I've got 3 good work examples, which I recently did through 3 different projects. So I'll get into a comparison of 211 and 33, which will give you a bit of an idea of where Working Group 211 sit. I know a lot of you all think it's very conservative. You're right, but there's a reason why it's conservative. So I'll get more into that details. I'll also go into a bit of a brief slides into selection of fenders, then fenders under mode condition. There's a bit of overlap with mooring analyses and how fenders react to a fatigue load from mooring. So I'll get into some of that. Then ship-to-ship berthing. Now, ship-to-ship berthing will be presented by my colleague Hari. Hari is also one of the contributors of Working Group 211. So he's reviewed and he's developed some of the sections over there. So I'll let him talk about it a bit more. And then finally, I'll get into component design, especially frontal panel. That's probably the main component in a fender system. Now, who is PIANC Working Group 211? Now, PIANC Working Group 211 is represented by a group of engineering houses, manufacturers, Trelleborg, Shibata, Prosotec, contractors, port authorities, Rotterdam, and Bramhaven from Germany. It's also represented by ExxonMobil, who brought the OCIMF Smarts into Working Group 211. Now, we've also got, I've got Bridgestone there. I know a lot of us know that Bridgestone is no longer in existence, but a lot of their people who developed the early days of the R&D of marine fenders have now joined CDIT in Japan and also Tottori University. So that's where we've sort of brought them together. We also had Professor Uda, who was also part of 33, sitting in a Working Group 211 to advise us on what got them to move towards the CE factors previously. So we've got all these people. So now, besides all these companies, there's been a lot of inputs from the wider engineering industry. So there's a lot of, I couldn't fit everybody in here, but there's inputs from different engineering houses. So I did send a couple of emails out while the working group was going on to just get feedback or to see what people thought. So a lot of that feedback has been fed into 211. Now, a bit of a background of working group, a bit of a background of Fender design guidelines. Now, in 1984, we established something that's called Bulletin number 45. Now, this contained a bit of guidelines on Fender design methods. Now, in my career, I did not get a chance to get intimate with this document, but I started off from here because I started working in 2001. So the first guidelines that I learned was through this guideline over here. You see, I think a lot of us are familiar with Working Group 33, which came in 2002, and it is still in use in present day. It's been there for 22 years plus, and 2 years in transition. Now, the new guidelines working group 211 was released in 2024, and it's meant to update or supersede working group 33. But there's a transition period that kicks off in May 2026. So between now and May 2026, we are still able to use working group 33 for new designs. But post May 2026, 33 is going to be obsolete, and there's going to be just 211. It's important to note that 211 is still going through minor updates. Of myself reviewed 211 and found a number of errors and a number of typos around which we are fixing. So the working group members have got a SharePoint page where we are marking up this document. So before May 2026, there will be a new version release. So look out for that. Now, what's the aim of working group 211? Now, 211 is there to ensure Fender systems are safe, reliable, durable, and cost-effective. Now, I know a lot of us will question the cost-effectiveness, but I'll get to it shortly. Now, it's also there to cover design, manufacturing, testing, and installation of Fenders. Now, working group 33 did not have any content on manufacturing, but we have got a whole chapter in manufacturing in 211. The reason why we introduced 211 manufacturing in 211 is to provide designers a bit of a background on what material cause what factors to Fenders. Now, for example, carbon black influences the Fender in a different way. Pure rubber, different, synthetic rubber, different. So this chapter is just intended to provide designers with the background knowledge of what each material is within built up of a Fender. Now, the new guideline also is not an update of 33. It's a whole new guidelines that is totally different. Now, remember the first working group meeting that was held in Port of Rotterdam in 2019. The first question was asked to all the working group members is, what are we looking at? Are we looking at an update of 33, or are we looking at an overhaul of 33? So I think the whole working group unanimously said that it looks like it's going to be an overhaul, because there's been a lot of development since updated within the guidelines itself or within the catalog itself. Now, I'm just going to get into a bit of a details on key takeaways for stakeholders who are involved with the design process of fendering systems. Now, what designers and engineers need to do or need to know is 211 is not a upgrade of 33. It's a totally different guidelines. Now, site-specific data is essential for cost-effective fender sizing. Now, it emphasizes more on integrated design of the entire marine structures and not just a fender. Now, there are factors that can be used within a fender system design if you are designing it for a monopile, because a monopile would also absorb some amount of energy. So the old guidelines don't talk about it or don't provide any guidelines. So engineers like me will draw a graph of energy absorption versus deflection and force just to work out how much of energy goes into it. Now, there are formulas in the new guideline that does provide some clarity in terms of that. Now, partial safety factors, it's a huge discussion point. Now, the old guideline has a table that we look at, and then we pick up a factor of safety and determine what the factor of safety is. Whereas the new 211 is a built-up of multiple factors based on probability of how the navigational condition of the vessel is, how the environmental condition is. So I think it's important for designers to be aware of this critical points up here. Now, what is it in for port operators? Now, port operators, now it promotes greater reliability for berthing operations. So there are instances that you will end up with a larger fender, but there's a reason why that has a larger fender, because there's a lot of probability, environmental or navigational issues or navigational factors. Now, transition, well, for port authorities, engaging with local pilots, tug masters, data collection would probably be a key takeaway, I would say. So I've dealt with clients before out just recently when I requested for site-specific data for velocities, it was not available. So that's something which I think as engineers we need to sort of encourage the collection of data, because that will further optimize the design process of fenders. Now, for manufacturers and suppliers, well, one thing is they need to update their product catalog to include approval testing as part of the 211 testing guide chapter. Now, fender systems must also meet the new testing standards. There's a whole chapter on type approval testing and verification testing that's detailed within the guideline itself. Now, collaboration with designers is essential to make sure that the industry aligns with the requirement of 211 as it's changed slightly. Now, project managers and procurement teams. Now, 211 is not a contractual document. It should be used purely for technical reference. I think that's a very key point. The starting chapter, there is a statement that clearly states that. Now, ensure specifications are clearly distinguished between 33 and 211. There's a difference in both the specifications. I think that's probably one of the first things we need to start developing as engineering houses. Now, beware of cost implication due to changes in fender methodology. I think that's another key point to be aware. Now, I'll get into a bit of a detail into berthing energy and navigational condition. Now, this is table 5.1, which is within working group 211. And there are three main categories that we look at now: favorable, unfavorable, and moderate. Now, if all conditions are indicating favorable, then favorable condition is met. Now, if there's one condition which is indicating unfavorable, then the unfavorable needs to be selected because that governs the design itself. Now, if moderate condition is selected, that means that it's neither favorable or unfavorable. So what it means is there's some operational categories that has got favorable, and there's some environmental that may be unfavorable. So if that scenario comes upon, then unfavorable needs to be selected in terms of the design process, unless we could mitigate the risk and bring it down to moderate. So there is some guidance in terms of how this needs to be selected within the guidelines itself. Now, navigation condition is very important. That navigational condition needs to be agreed with asset owner or developer before starting the Fender design. So this needs to be very clearly stated in a basis of design and agreed with an owner. Now, if two or more unfavorable factors are present, a detailed study is recommended, ideally to confirm the control and define a safe environment threshold within the operational and environmental condition. Now, for operational impact, it's to be noted that unfavorable condition may also affect mooring and loading safety within the berth itself. So this table provides a detail on what operational interfaces are within the environmental condition. So this needs to be established very early in the design phase. Now, I'd like to sort of highlight key findings of PIANC Working Group 145. Now, 145 states historical data suggesting a correlation between berthing velocities and berthing vessel sizes can't be confirmed. So therefore, applying these velocities curve for large vessel and large seagoing vessel may pose a safety risk in terms of how they are used within the design itself. There's also no evidence between berthing velocity. There's no evidence berthing velocity is directly influenced by the vessel type of marine structure, type of fenders system, UKC, and also tugboats. Number of tugs assisting the vessel into the berth. So there's no correlation between the velocity we've used. There's also no direct correlation between environmental factors and berthing velocities was found. Now, berthing velocities strongly depend on berthing procedure itself. That's probably the biggest contributing factors according to 145. Now, that depends on the landing, the experience, as well as the training of the pilots, and whether it's tugs are present or not, regardless of number of tugs, and also what berthing systems that you've used, whether there's a monitoring system or there's a control within the vessel that alerts the pilot when the vessel is brought into the berth itself. Now, ideally, we recommend the use of site collected data. Now, a few days ago, I was talking to a colleague and I was asked a question, how much of data do we need? Do we need 1 month of data, or do we need 10 years of data? I think that's quite an interesting question, because it's not defined in this document. But what I would do is I would collect a series of data within 6 months. I would think that would probably be an ideal period of time. And there will be a peak and there will be a trough down there. So I'll go with the mean value of berthing data. So that's the general understanding with this approach. Now, if no information is available, the designer can use this table. Now, velocities are not slightly, but they're very conservative on this table, I think. If you can see under the unfavorable condition scenarios, we can get up to 0.25 meters per second, which is a very high speed berth, which is quite rare, but it is quite likely. So, and I've got a table down here that indicates this is mainly for longitudinal berth for ro-ro vessels. Yet again, the numbers are pretty high if there's no existing data collected. Now, just another point, I've also been asked, if you're looking at a greenfield berth, a new berth where no data is present, what do we do? Are we Are we looking at a very conservative design? Well, the answer is no. Now, when I talk about data collection, it's very subjected to an environment or a specific location. If we can obtain berthing velocity data around the vicinity of a harbor or a port or something which is just by the side of what we're building, that data counts for berthing data velocity as well. Now, provided the vessel types are similar class or the vessel types are similar type. Now, I'm just going to quickly summarize the energy side of it. Now, 211 describes berthing process for a large vessel more accurately than 33. So we'll go back one step. So if you look, there's no vessel here. So we looked at a series. So within the working group, we had Dr. Robus, who's looked at all that vessel sizing influence of each vessel and had a big data. Collected quite a lot of data from Port of Rotterdam in terms of comparing vessel sizes. What we've realized is the velocity data that we use today more accurately represents 33, more accurately represents a larger vessel. So in other words, whatever that comes out from Mr. Brolsma's curve is perhaps too conservative for smaller vessels, which has been used within the guidelines itself. Now, correctly using 211 will provide the berth with optimal fenders because, as we know, our velocity is the highest. It's exponential in the formula, and it does affect the berthing or the energy absorption quite significantly. Now, often slightly more economical under the working group 33. Now, correct use of means, correct use of local data and experience is used as much as possible in terms of developing the velocity caps or the velocity of a vessel. A designer should always talk with the potential users like harbor masters and port pilots or port authorities to collect this data. And that's why, again, I repeat this, that we need to collect a lot more data to use 211 and optimize it further in terms of getting the right design, right fit for our project works. Now, there's also a table on berthing angles, which I believe is not present in 33. Correct me if I'm wrong. Now, berthing angles have been looked at, and these are also based on data collected on how vessels approach, whether it's tug assisted or whether it's operational driven. Now, it does affect the energy of the fender system that the fender needs to absorb. The angle of the vessel does have a bit of an influence there. Now, incorrect angle assumptions can often lead to damage of vessel hull or fender units or even the berth structure, because fenders are spaced at a certain distance. So if a vessel comes in a wrong angle or an inaccurate angle than what was designed for, there's a chance that the vessel will make contact with the structure and damage itself or the structure. Now, influence of fender selection and placement determines the type, the layout, and also the fenders that we need. So in the event we don't have any data on approach angles, we could fall back to this table 5.5, which provides some guidance on what a vessel approach angle could be within the port. Now, partial safety of factors and probabilistic design approach. Now, it's very clear that the guidance on adjusting the berthing energies, but specific berthing conditions are related to partial safety factors. The variation in vessel size within a berth. So if we're going to have a huge variation in vessel berth, that will contribute into the factors that we use, the built-up of factors that we use within the partial safety of factor. Now, safety classification of potential consequences of fender or failure as well. So there's an ARI, or there's an annual return period for vessel approaches within the berths, which needs to be plugged into the equation, which spits out a a cocktail of factors that we multiply within the factors of safety, probabilistic factors of safety. Now, the new 211 accounts for uncertainties in fender performance. That 10% that manufacturer's tolerance that usually comes in is also built into the factors. Now, having said that, that still needs to be used when we multiply that with reaction force. Now, it considers multiple fender contact. Now, in the past, what I usually do is I usually look at the shape of a vessel or flare angle coming into the structure, and I geometrically draw and determine what the percentage of deflection each fender is taking. Then I work it out back through the performance curve to see what the energy absorption is. Obviously, the reaction would peak up at 30%, but what the energy absorption is. But in the new 211, there is a totally separate table that covers multiple fender contact, and there is a reduction in fender use. So we don't need to go back and do that analysis or detailed analysis on multiple fender contact, but just pull out a factor which is stated in a table. Now, overall benefit is 211 has got more transparent, practical, and user-friendly guidelines compared to 33. I know a lot of people won't agree with user-friendly, but I think it's a matter of just getting used to the new guidelines. When I graduated as an engineer, I was taught with the old 33, and I'm so used to old 33. I think a lot of page numbers are pretty much familiar to me and how to get to things. And until today, I still struggle to find things within the new guidelines, although I was involved with it. I think it's a matter of just getting used, and that's what I like to sort of get everyone up to speed or encourage people to read it or to use it as much as possible. Even though if your project work doesn't demand the use of 211, please work out and see if there's a way you can try to compare your current guidelines with your current design with 211. Now we've moved from the deterministic approach to probabilistic approach with this one here. Now you can see I've got a list of tables on the side there where it corresponds to conditions from A to D. There's an E as well, but E is not stated on this table because that pushes the factors way too high. We're not meant to be designing on E. And then coming back to the navigational condition, which I had table 5.5 previously, where we've got favorable, moderate, and unfavorable. Now, we've also got two different tables in here, which caters for multiple fender contact, for partial safety factors, and also a single fender contact. Now, these factors were derived on the basis of 1 in 100 births per year, and that's how this was worked out. Now, there's been a lot of work that's gone the back of this factors development within the working group members, crunching up and comparing it, drawing graphs, agreeing to disagree, and all this stuff. There's a lot of work has just gone back here. Now, we do agree that this set of numbers are very, very conservative, but this would be the ultimate worst case scenario if we don't have any site-specific data. Now, if you plug in site-specific data, you'll suddenly find your factors dropping up very, very low. So if you look at, for example, look at condition A, reference A, you start off from a 1.3 factor, which is pretty low compared to what we've got in working group 33, which is 1.5. But under the same vessel condition, if you go all the way down here, you're looking at a 1.8. So there's a big change in some of these factors, depending on how much of information, how much of data, and how we understand the vessel to come into the berth itself. Now, oh yeah, just gonna go back here. So A, B, C, D, which you see on the screen here, correspond to this table over here. Now, I did say that E is not included. Now, E is a very high risk of loss of human life. A vessel shouldn't come in every time and risk people's life in a big way. So what we have said is that's this classification is beyond these guidelines. It's not covered under here, but we are able to pick A, B, C, D from the approach. That's all right. Everybody can hear me in the back there. Right. Good. Prefer not to hold something. All right. Okay. This slide talks about the different ways a fender design is undertaken. And a lot of people, including myself, are very familiar with this way, where you've got the E equals to half mv square energy calculation. And then we've got a series of factors of safety. Now with the new 211, you will realize that we've taken out toughness cushion factor out from the equation. So this is the new 211 calculation. Now I'll just go through 33 very quickly. It's taking out the energy absorption, multiplying with a factor of safety, then getting out the fender unit. But with 211, there's a huge factor of safety with an 8-step approach, which is usually adopted. A bit longer, but this is pretty much what gives us a probably safe method of trying to develop a safety factor. Then the fender is selected. Obviously, all the adjustment factors that we've got for the multiple fender contact. So this is basically the summary of the design methods between 33 and 211. Yeah, now I'm going to get through a couple of details in terms of scenarios of birds. Now, we recently undertook 3 different projects. I've not put any names here, but these 3 projects has got different consequences classes, and you can see that we have already indicated the navigational condition based on discussion with the asset owner. Now, there's also presence of tug, non-tugs, see under scenario 1, 2, and 3. And then we've got a Panamax, cape size, and a handy size small vessels, which is pretty much what we've got. So these are the details of those vessels. So I'm going to focus on scenario 1 first. Oh, sorry, I've got this one here. But before I get into that, we've also put in here the site-specific data. Now, for scenario 1, we didn't have any site data, so it's pretty much going to table 5.3, which gave us a 0.2 meters per second velocity. But for scenario 2, it's 0.15, 0.16, which were determined velocities or limits set by the port authority, or even 0.6 were based on data collection. So berthing angle that we've got for scenario 1 was pretty much 10 degrees. Scenario 2, we had 10 degrees, which was determined by the port. Scenario 3, this guys didn't have a berthing angle, so we went to table 5.5. Looking through the navigational condition, it was recommended as a berthing angle of 8 degrees to be adopted, and that was accepted by the port authority itself. So the partial safety factor which we came up with is 2.4. Only to compare this with scenario 2, which is 1.87 with data, and 2 with data over here. So this is how we develop the scenarios. Now the berthing energy that we got is here, but you can see the fender sizing that we've got: 1.6, 1.8, 1.15. So we take one step back, keeping in mind that scenario 2 is the largest vessel, second largest and smallest vessel. Now what we did with that is we did a comparison between working group 33 and working group 211, and you can see the difference in fender sizing. There's 2 times SEN 1.4, 2 times SEN 1.6, and I was myself quite surprised to see the difference in the berthing energy, which is humongous. I had to double check my calcs just to make sure I didn't make any fundamental flaws. But obviously, you take the velocity square times with the factor of safety, you're looking at about 2.4 times higher value, and that's how this pretty much ended up where it is. So in this case, you can see the fender size change from SEN 1.4 to SEN 1.6, SuperFen 1.6. So, well, yes, we agree 211 is very conservative, but I think the message here is there's no site-specific data. I'm going to go into scenario 2. Now, with scenario 2, we had site-specific data which we used. Now, the berthing velocities were pretty much the same because this was used. This is what Mr. Brospa recommended us, and this is what 211 came up, sped up. Berthing angles were also the same, so it's a good comparison. And then If you look at the partial safety factor, the partial safety factor is pretty high because of environmental conditions. So on this particular example, we were bringing the vessel in a very exposed condition. So you can see the difference in energy caps that we've got in here. And what this results is pretty much the same size fender, except we've got a fender with a higher grade on the 211. So this is a good comparison of 211 and 33. Also considering the tugs, there's no thrusters, and also navigational function, which is quite moderate. And now this is perhaps a good example. I like to talk about this example. Now this is a small vessel, but I'm going to go to the outputs first. You can see the fenders on the 211 ended up being a bit smaller, tiny bit smaller than what we developed in 33. Now, again, despite having a higher factor of safety, which came up from one of the tables, our berthing velocity was pretty low because we had a fixed or provided berthing velocity, a data that we could rely on. So in this case, I'm convinced that the fenders that we've looked at here did save the client a bit of money on the 211, but it did represent the right, the more accurate fender size. Now, I think based on these three scenarios, I like to sort of add that 211 is a very temperamental guidelines. It's a very sensitive guidelines to navigation and environment. If used in the right way or with the right data, you would get a more well-represented design overall as compared to 33. And that's pretty much what we found from these three scenarios. Okay, I'm going to move to the next part of the presentation, which is selection of fender system. Now, I believe some of this data is available in the old 33 guidelines, but the new guidelines provide a bit more graphic in terms of what we need to do. Now, I've gone through the design energy absorption side of it. I think once that's obtained, identifying the type of fender is the next challenge. There's a lot of guidance within 211 on the type of fender, given the type of vessel and the type of berth that you've got. I'll get into a bit more details on top there. And then once that is developed, once the fender type is taken up, grade is selected, and we come up to a base performance. A base performance is pretty much what we find in a manufacturer's catalog. That needs to be factored up with manufacturing tolerance, temperature, velocity, and angular factors, which come down here. And then if there's any need for multiple fender contact, this is where you actually apply that multiple fender contact. And sorry, this is where you actually multiply the fender contacts, blue and blue. Now, in 211, applications for different vessel types and a selection of fender has got, it does vary on the vessel type. It does vary on operational factors and also experience of the pilot that's bringing the vessel in. And also it does look at the site-specific data. Now, this is two fantastic tables in 211, which talks about the application process. Now, it gives you a scenario of whether the vessel comes in with belts, and it gives you a whole sort of option of the types of fenders we can potentially look at it. So if you're looking at developing a new berth or a new greenfield project, and if you've got a sort of structural form developed, or if you're looking at a structural form, this gives you a bit of an option on the types of fenders we could potentially put on the structure, depending on the vessel hull and all the stuff. The same thing over here. This talks more from an angle of types of vessel. This talks more from the angle of an application of the vessel. So these tables were directly plucked out of 211. So this provides a bit of guidance on the type of fenders we generally take. and what we should avoid for different types of vessel, different types of operations, and different types of uses at the berth. Now, if there's a berth which is multi-user berth, now that there are some overlaps between fenders that we can sort of go. I think Adam will probably cover a lot more on this on the types of manufacturing of these fenders a bit later. Now, selection of fender, obviously been through a bit of that base performance versus characteristic performance. Now, base performance is a data which we collect based on the velocity of 2 to 8 centimeters per minute. That's a very, very slow speed compression. So base performance is what we see in some of the Trelleborg catalogs where you've got the CV value. So these are base performance. So the RPD performance is usually multiplied with 0.15, 0.15 meters per second. Now that's based on a higher speed velocity. Now, what I usually do is I'll design the fender, and then I'll go into a CV value fender, pick up a CV value, and I'll multiply that with angular, temperature, and also velocity factors to get the right energy absorption we need for our structure. And also that same thing is multiplied with the reaction as well. Now, property of a particular fender needs to be based from the manufacturer itself. Now, different fenders have got different form factors. So very often the velocity and the temperature factors do vary from one fender to another fender. So correct me if I'm wrong, even in Trelleborg, different forms of fenders have got different factors, which is pretty much obtained through a type approval test. These numbers are actually taken out from there. So please be careful. You can't just take one manufacturer's factor and apply to another one, because that would be a fundamental flaw. So that's very important to understand. Now, the CV factors in working group 33 are value as tested, because these are the ones which are factored by 0.15, whereas the CV values, which in some catalogs take, that's without any high-speed testing velocities. Now, there you go. I've got the correction factors over here, which represents 3 main factors. Then multiplication of multiple fenders is also done at this stage over here, and we get the design of what the overall energy and also overall reaction is for the structure. Now, fender under mode condition. Now, as far as I remember, working group 33 do not cover this as detailed as it should be. Now, it's important to understand that fender systems are typically designed for berthing, but they also need to be evaluated under mooring suitability, especially on lean-on loads. So if, for example, if you've got a berth where you're going to get a vessel coming in, and the vessel is going to hang around for 2 months before it departs, the vessel is going to be subjected to wind, to currents, to waves. It's going to be subjected to possibly passing vessel around it. There's going to be an often roll of the vessel against the fender. So that's probably quite critical, because that results in a lot of fatigue load on fenders. Now, I've got this little picture here. I don't know where I got it from, but what that indicates here is there's a bit of a fracture on the fender over here, with the vessel board in front there. Now, I've seen videos of fender failing under mode condition when a passing vessel passed through. Now, there's a video that I was given. I was showed by Port of Rotterdam, doing a bit of research on passing vessels, and they wanted us in the working group to be aware of the dangers of mooring loads, and that's why what we have done is we have introduced a lot of content on a mooring mode vessel at berth, that it needs to be done. Now it's important that we mount these fenders and we undertake a dynamic response analysis if a vessel is meant to be on the berth for prolonged periods of time. Now, evaluating how the fender behaves on a time-varying load, similar to earthquake loads. When we look at earthquake loads, we look at a time history. We do a time history for vessels sitting at the berth, just to understand how much of wear and tear the fender undergoes. Now, there is also a test that that is called durability testing. It's a cyclic test where I think the guidelines currently recommend 10,000 cycles. So if you are buying fenders from a manufacturer and you are determined that the fender is going to be compressed, for example, the fenders that we have along Brisbane River for the city cats, they're compressed like 100 and thousands of times in a year, because a city cat operator comes in and smashes into the same fender every time the vessel comes in and out. So that's an example of very heavily used fender. So if I was, I would not say if I was, but I would probably subject those fenders to durability testing. Now, durability testing doesn't mean you take the actual fender and you test it up. I think Adam will probably cover this a lot more. It's getting a scale down size fender with the same rubber source that the real actual fenders are made. And then testing is done, cyclic testing is done on that. So that would sort of mitigate some of the risks in terms of fatigue and durability. Now, fender under mode condition. So we need to ensure that peak fender reaction does not exceed the hull pressure. I think this is a very critical point over here. Now, this is built up of what the catalog values provide us. And then there's a hull, which typically is between 200 to 400 kPa. And then there's a sizing of panel that we need to do, which I'll get in a bit more detail shortly. So I think it's very important for us to assess the mode condition through the hull pressure or the pressure that we transfer through the thing. Now, nonlinear fender behavior impacts the performance of fender under cyclic loading. I think I've covered that. Now, I've got this little table up here which indicates the process of going through this. Now, chapters 5 to 6 provides you what the project specifics is. We design the fender over here, then the fender goes back into a loading analysis, a dynamic loading analysis, and subsequently we move up here, see what the project requirements are. If the loading analysis suggests that fatigue is not a problem, then at the end, fatigue is a problem, fatigue goes back to a different fender size. That means we've got the wrong fender size, wrong grade. We've got a lot more stress within the fender, which needs to be revisited. So this is one of the tables that came out from figure 7.1 in terms of a design flow for mode fender condition. Ship-to-ship berthing. Can I get you on?
Yeah,
Do you
sure.
want to talk about it? I'll hand it over to Harry to cover some of the stuff.
When WG211 had a meeting in early 2020 in Melbourne office, so I had an opportunity to present to them the ambiguities that the WG33 and other guidelines had in terms of calculation of berthing energy for ship-to-ship berthing. So since then, the WG211 had considered revising their section and slightly adding more details, maybe clarifying some of those ambiguities among other sections. So this particular WG211 has the berthing energy calculations for a case of floating storage regasification units, but in relation to the other cases such as vessel to dock, it has we have other reports such as OCIMF or MEG4 talks more about the ship-to-ship berthing. So the two important factors for calculation of or selection of the fenders are the relative velocity of the approaching vessel with whatever stationary vessel. And also another one, which is the key in most cases, will be the governing one, is the stand-up distance. So these two depend upon number of factors, such as the size of the vessel and also the weather conditions, because of which the relative velocity changes or need to be considered carefully for sizing up the fenders. So WG211 has a combined vessel mass coefficient that is calculated based on the displacement of individual vessels involved in the ship-to-ship operations. And from there, there is a table that talks about or that lists what is the minimum stand-off distance and also the minimum number of fenders, and typical pneumatic fenders, 50 kilopascal pressure capacity needs to be for that combined mass coefficient arrived based on the expression provided in WG211. I think, yeah, that is it pretty much. Yeah.
Okay. I'll jump to the next slide. Next one here. All right, component design. I've not gone into too much of details, but I want to focus more into our panels. Now, this 211 looks at the whole design from a holistic side, where we look at an integrated design approach. So there are details and requirements for fender panel, chains, speedy pads, and also fixing details, which must be designed as an overall system. Now, I know a lot of us would question, fender panels is a steel design. Aren't we supposed to be following the Australian design codes to design it? Yes, you're right. But I think the guidance that's provided for fender panels it pretty much talks about the fender panel being a box section, a closed box section. So nobody in today's day design an open section. I'll be surprised if someone does it, but that would encourage a lot of corrosion, a lot of durability issues. So things like that. And there's also some guidance, if I'm not mistaken, on pressure testing for fender panels. So structural compatibility is another area which we looked at.
To use this,
My voice getting a bit weaker.
Yeah.
Yes. Can you hear me? All right, cool. So structural compatibility is also another area which was looked in a bit more details, where we looked at, for example, if the fender is berthed onto a monopile, we need to have enough of real estate to mount all the accessories. We need to have enough of opportunities to get a maintenance worker in to inspect stuff. So these are some of the guidance which are given within the component design. Now, poor component design or structural mismatch can lead to reduced durability, which will either reduce the life cycle of a fender, or it will cause a failure of a steel on site. Now, here you go, panel. So key consideration for designers. Now, ensure there's proper contact surface area between high tide and low tide. That's where the vessel covers from one end to another end. And then account for uniform line loads. Very often line loads are very concentrated. So that's something which a designer needs to be aware of, where these line loads, at what tidal range the line loads are going to be in contact with the structure. Now, the next point here, match berth structure with fender system, is pretty much what I just mentioned. We just need to make sure that the fender is not only able to be mounted on a structure, but we've got enough of room to put chains, we've got enough of room to put accessories and maintenance access and all this stuff. So again, vessel contact varies. There's belts, which I've spoken about. Next one. Now, positioning of fender panels. Now, we need sufficient contact area to limit hull pressure. That's probably a given fact that, we need to look at that. But it needs to be able to accommodate the rubber unit, and then consider transport limitation for whichever projects that we are looking at. Now, the height of the fender needs to cover a full tidal range. Obviously, prevent belting from riding over or under the panel, whether we go with a rope guard or a belt guard or something like that, or the fender panel needs to be long enough, and it also allows for wave effect and vessel movements. So that's another critical thing which needs to be considered when sizing up the fender panel. Now, align the top and bottom of the fender with the freeboard and also the bird structure to provide enough of protection to the bird structure and also the fender, the vessel. And obviously all the mooring lines and snags that needs to be checked with the fender panel. So structural integration is another area which we have covered in 211, where we look at match panel size with the rubber dimension. So it doesn't mean that we've got a big rubber or a small rubber, we go with a sizable panel size, but it needs to be compatible with the fender itself. Now, the use of multiple rubber units is, if it's needed, then it needs to be covered for longer or taller fenders. And obviously, the last thing is apply some engineering judgment experience to make sure it's proportional in design. Right, so this slide here talks about transfer of fender loads to a structure. Now, during the working group sittings and meetings, we had the opportunity to engage with people who build ships. I think we spoke with Samsung and we spoke with another shipbuilder in Korea. Now, we did ask them in terms of what's the build-up of a vessel, what's the hull pressures and stuff. And I'm not joking, when we provided them what we had in Working Group 211, they felt that that was very conservative. So the hull pressure that you look up here, you see has been changed pretty much. Some of the hull pressures have actually gone up quite high, especially for the smaller vessels. But I've been also questioned about this category here, the bulk carrier. The hull pressures are flipped the other way around. So again, this hull pressure came out from shipbuilders in terms of what their limits are, and that they have actually looked at stiffness within the hull of the vessel itself. And that was the table, or that was the data which we got from shipbuilders. So we did query them on some of this stuff, but they were determined that's what the vessel is capable of taking. Now, if we have got a number of vessels of different types in here, I would go with the smallest hull pressure, just to make sure we have got a variability of different vessels, or we don't damage the big ones or the smaller ones. Oh yeah, legal stuff. I'll just the next one. How do we get to the next? That's pretty much the end of the design module. I'm just going to, how much of time do I have?
Yeah, it's difficult, isn't it, to shrink that down to 45 minutes session?
Yeah. So I've got another risk management module. It's only got 500 slides. We're done. All right, session 2.
Are you okay to continue? Or?
Let's continue there.
Okay, yeah. So let's do this. And we are
Let's continue and get the pressure off.
Yeah, 15 minutes behind.
Yeah. Okay. All right. Session 2. I think the first session was covered mainly for designers or people who carry out the technical work. But the second session here is purely based on risk management or asset owners who think that, who wants to know more about what's within Working Group 211. So what I've done is I've taken out a few sections, including sustainability as part of an asset user requirement. I think it's not working again. Harry? Oh, okay, good. I fixed it. So this section here talks about responsibilities between owner, designer, and manufacturer. It talks about the importance of testing and break-in cycle. That's a very, very key thing, which is covered in the guidelines. It talks about warranty and product liability. Why is it important? And then obviously the green stuff here, which is sustainability of fenders. Now, I believe the next sessions will be a bit more detailed in terms of interface of manufacturers from designers, but I just want to cover a bit of overview of what these responsibilities are. Now, an owner or a designer's responsibility within a fender system design is defined by the requirement of specific data. So an owner needs to make sure his designer or her designer covers vessel details, berthing velocities, tidal variation, and environmental conditions very clearly within a spec or a basis of design. Now, the spec performance criteria in terms of what the minimum energy absorption required is, just to make sure that we know what the velocities correspond to, and also what maximum reaction force. So that needs to be very clearly stated on a drawing or a basis of design. So the durability requirements and safety margins that was assumed. Now, as we understand that the fender is not only a fender by itself, it's integrated with the whole structural ecosystem at the back of the fender, which transfers load onto the structure. Now, it's important to also define what the structural form is. So a manufacturer picking up the design and reviewing it would understand what the interfaces and what the limitation are. And I think it's also important to define how the vessel comes in, whether we've got multiple fender contact or single fender contact. So, and I would encourage very, very strongly for owners to be involved in review and approval process, including the testing process, because that's a key item in the design and supply of fenders. We need to know what the fenders are capable of before putting it on our birds, because there's a lot of stake when a vessel comes in out of control in terms of damages to vessel or even structure. And a manufacturer's responsibility, I think they'll probably cover a bit more later on, but it's to make sure that the design is compliant in terms of validating the design and the material properties specified by the owner. Now, testing and certification is a very key part of fender design. It is something which I think needs to be observed very, very closely. Now, all the type approval testing that we get from manufacturers need to be reviewed, and all that verification testing that is done on the actual fenders need to be reviewed as well. I myself I've been involved in a couple of fender testing campaigns for a few people, and I found a lot of gaps in some of these areas. Well, not major ones that fenders are rejected, but I found gaps where things can be improved a lot more, and I think the guidelines does cover some of these aspects. Now, manufacturing quality is the other thing which, as I say, is incorporated within the guideline itself. We've covered manufacturing just to give a designer or an owner an idea of what materials trigger what effects within the fender. And that's also very, very important, that we need to review all the stockades, all the raw details, what type of rubber we're going with. So it's good to have that reviewed as well. And then obviously a manufacturer's responsibility is to support all the documentation in a very nicely bounded copy with a red ribbon to an owner to say, this is what your fender is capable of doing and this is what we've supplied you. So in 211 under table 13.1, there's this table in here which very clearly talks about the responsibilities. Now this is embedded within the specification writing section within 211, but it clearly gives there who does what and what the obligations are for each. There's a lot of stuff for designer and contractor in here, but a supplier would probably have some interface with the designer over here, and they've got their own manufacturing and testing sections down there. So I won't get too much into details, but this is basically a compliance from a risk management perspective to make sure that the performance are met within a fender design and the durabilities of the fender is there throughout the life of the intended life of the fender. Now, asset owners, this is probably a very, very important topic now. Specific testing requirements for all, specify testing requirements for all fender type. I think it's very important for us to note the percentage of fender at least within a specification to highlight how many fenders are we testing and what the durability testing is. Now, there's something called break-in cycle, which I often observe a lot of specifications, including the ones that we produce internally, does not have these break-in cycles. I think that's a very key thing. And 211 talks a lot about this. Now, for those of you who are not familiar with fender testing, there are 4 cycles. A fender is subjected to 4 compressions. The first compression is always called a break-in cycle. The second and the third compression is stabilization cycles. And the final one is performance cycle. So the final compression of a fender, the record from the final compression is taken as performance data. Now, the reason why we break in the fender first is whenever a fender is manufactured, a fender has got, it stiffens up. After the vulcanization process, it stiffens up. So I've seen personally the first compression of a fender can go up between 20 to 30% of the reaction force, the design reaction force. So that's like putting in a 1.3 factor. So imagine if you take a brand new fender without breaking it and putting it onto your structure, what happens is the first impact of a vessel, you'll get a huge factor of safety getting into it. And worse still, if the vessel comes in out of control, that increases the factors of safety. So I think it's very important we include braking cycles within our specification. Now 211 recommends braking cycles for every fender, not only the selected fender. Every fender needs to be broken into. Now typically we take 10% for performance, but some project requirements may call for 12 or 15%. That's entirely up to the project owners and the requirement. Now testing must be validated to the catalog performance. So if we go and design a fender to a catalog performance number, when we test it, we need to validate that against. And that's where I think the presence or the involvement of asset owner is very, very essential in this process over here. Now, witness critical tests, there's often a third party representative who comes in and check the manufacturer or witness the testing process. Now that third party could be anyone who is familiar with what fender testing is all about. Now I've personally done that a couple of times. It's nice to see a fender getting smashed, although it's quite slow. It's not full speed, so it's a good experience. If any young engineers wants to get into fender testing, please put a hand up. I think a lot of asset owners would probably be keen to get people on sites to actually look at this. Now, it also minimizes risks in terms of bias and inaccurate test results. I think part of the testing scene is to inspect collaboration certificates of all the press machines, temperature gauges, all the different kinds of serial numbers these fenders have, and how do you determine which is your project, which is there's a whole heap of things to be done on site when you go and look at this. Engage a reputable third party with a proven expertise, obviously, to reduce liability and risk for your project, and also a direct involvement in risk which is non-compliance with underperformance fenders. Now, testing is not limited to rubber component. The panel needs to be tested. Sometimes the chains are tested. Now, there's also a lot of tests requirement for foam and pneumatic, but I think 211 does not cover testing for foam and pneumatic because ISO standards cover a lot of this requirement. So 211 committee didn't want to overlap with ISO, so it has a reference directly to ISO. Now, why is documentation and traceability very important? Now, obviously, it mitigates risks for substandard or non-compliant materials being used within a fender build-up. So there's different material testing, there's TGAs, there's all this stuff. So that's part of traceability. Now, it prevents changes to production facility to avoid variability in poor quality contract. Now, if you've got a project with 4 fenders, there's a good chance you get rubber source for all four fenders from one main supply. But if you've got a project with 80 fenders, then there's a good chance you're going to get 8 different supply of fenders. So in terms of testing it, I would recommend pick one from each source randomly and test it, because that gives you a bit more confidence that, all right, the quality of rubber that I got from all sources are reliable, and a vessel can come and hit any fenders without me losing any sleep. So that's what it is. So it reduces the risk of performance deviation due to an unverified material, and then proper testing also prevents premature failure and costly downtime for your operation. So it needs to be supported with, obviously, procurement and long-time asset reliability. Now, key specification requirements are warranty period. That's without saying that's very, very important. Now, it also needs to be specific considerations on vessel type and berthing requirements, characteristics, environmental factors, and then it also needs to be retesting, include details on testing, retesting if performance are not met. So I'll give an example. Some specs are written in such a way that you've got you shall test 10% of your fenders, and if any non-compliance are found, then you shall test another 10%, or you shall test another 20%. And if any non-compliance are found, you should test the whole lot. So a lot of specifications need to be tailored that way, which will give a bit more confidence to an asset owner that, look at this is quite important. We need to make sure that the fenders are compliant. Now, what are the risks and impacts to to poor fender specifications. Obviously, it's unspecified warranty. That's going to result in a lot of disputes over performance and failures. Inadequate insurance from the manufacturer will result in some financial exposure and accidents and damage and claims and all that fun stuff that we usually see when things go wrong. And then substandard material risk would provide some would result in reduced energy absorption for safety hazards. And then design mismatch, obviously when you get the fenders on site, they don't quite match and they are overloaded with a lot of additional reaction force, which in terms pretty much causes the structure a lot of issues. Now, operational disruption probably is a big thing for a lot of asset owners who can't afford any downtime. So that sometimes can be solved with just covering yourself well enough in the specification, increase of life cycle costs throughout the design life with all that OPEX cost that comes in, and then obviously legal and reputational damage which comes along with the specs. Now, sustainability. Now this is a topic which is growing very, very fast, and I think there's a lot of Australian ports who are also looking at sustainability now, reuse of recycled material and all this stuff, which is quite good, quite important. So 211 does cover aspects of this. It's a growing focus within PIANC itself in pushing a lot of sustainability, not only for 211, but for multiple other guidelines which they're producing. Now, increasing a number of ports require sustainable design in a number of investment. It's probably I don't know why I put this point in. I can't relate to it, but evaluate the full life cycle of a Fender system, which considers material sourcing, manufacturing, operational, and end of life recyclability. I think the session after me would probably get a bit more into details in terms of the manufacturing process and the material sourcing in terms of how much of percentage of this is recycled and how much is pure rubber. Now, challenges in sustainable disposal. Before we move forward, I've spoken to a couple of port owners in Europe, and I was pleasantly surprised there's been a bit more development in terms of what fenders are used for. There are some people who some ports who take old fenders out and they reuse it. I've seen arch fenders used as benches in a park, which is quite an interesting concept. I've not seen that. I've got a photograph, but I've not put it up here. I've seen fenders. Another port owner said that he used his old fenders to submerge them in the sea to create corals or habitat for fish. So that sort of option. So that the guidelines do not limit what we do with this, but I think there's a bit of innovation required. I think in the next 5-10 years there'll be a lot more discussion on sustainability, reuse of these fenders. Now, there's also I think before we get there, there's a cost factor which we need to solve. It's not cheap to dismantle a fender like a car tire. There's a lot of steel bits within a fender. There's a lot of components and strands that needs to be ripped off. So that amounts to a very high cost. I think they can relate to it. But I think over time, it needs to be done. Somebody needs to come up with a process where we can abstract this material out and reuse it again. And I think that's probably something which is a developing sort of technology. Now, some current disposal practices, many ports store fenders indefinitely in their backyard, and some fenders are disposed via landfill. Now, I've got a fender at home. If anyone's keen to come and have a look, it's a bit too heavy for me to bring it here, but that's pretty much what I do. Go to an old port or go to old facilities. If you're not using the fender, can I just buy that? And the chap said, I just take it away when you get rid of it. So put it in my car booth, and I brought it back home. So I've got an SCN 300 at home for those of you who wants to come and visit me. So I'm just going to go to the next one. So sustainable, I've got the last slide over here. So again, sustainability is increasingly an important factor for manufacturing. Again, I think manufacturing is going to change in the next few years. There's a lot of R&D which is going on with a lot of manufacturers considering recycle or synthetic sort of base product which can be reused later on. Again, I would say for now we've got a good blend of mix. I think Adam will probably cover this in a bit more detail in terms of what goes into a Fender and possibly what's coming in the future as well. Now, all parties involved in Fender system selection, design, and production should contribute to improving sustainability, including designers. Like people like myself need to go in and say, all right, what if we can do that? What if this? Because that opens up to a whole lot of opportunities, not only for asset owners, but also for manufacturers and also design innovation. Now, despite of limitation, smarter material of choice and engineering practices can clearly reduce environmental impacts. Legal stuff. Thank you very much.
Thanks, Harvinder. You recommend converting the old fenders to tea tables and benches?
Yes.
Thank you. I think we are back on track. However, with your permission, Harvinder and Sam, can we allocate 5 minutes for the question and answer session? Thank you. Any questions?
All right. Yeah, go on.
Possible, yes, for the recording.
I just wanted you to clarify, you mentioned something about the manufacturing tolerances included in the design portion.
Yeah.
Is that so we shouldn't be adding the 10% reduction on to the energy?
No, we should be. We should be adding. Yep. I think that is just a probabilistic approach of what the built-up factors of safeties are. But you still have to add that to your energy absorption and also reaction forces.
Both. Yeah. Okay. Cool.
Yeah.
Thank you.
Just to clarify too, there are different percentages for different types of fenders as well.
Correct.
So, all right.
Thanks, Harvinder. I just have a question about replacing fenders on existing burrs because fenders don't last as long as burrs.
Yep.
So what is the anticipated changeover if we have a certain fender and the new guidelines kick in? Can we just replace the fender or should we go through the calcs and potentially have a mismatch?
Well, I think Anand, that's a very very good question. I'm also dealing with one such scenario at the moment where I've got an asset owner who wants the best latest and the best guidelines for their replacement. Now, what I would say for that is, I think first of all, an existing infrastructure has got an existing template of fenders, so you're going to be limited to the type of fenders. So most likely you're going to end up with the same fenders. But I think what I would do is I would assess that, do a comparison, a sensitivity between a 211 and a 33 and see what the significant changes are. You'll be surprised. You'll end up with the same size fender with just a different grade, which might suit the berth. But if you end up with the fender slightly bigger, then you need to reconsider the operational requirements with your asset owner, or either your limit some of that operational navigational to the berth. So yes, please, I would say try it out, test it out with 211 and then see where you go from there.
Yeah, hi, thanks, Harvinder. Just a question on the practicality of getting the site-specific berthing velocity data. Now, I understand that a lot of that work was done in Europe, where they fairly advanced and probably have more access to that data. But in my experience in Australia, it's very difficult to get that site-specific data. So yeah, have you got any comments on that or any guidance to give people on that in the Australian context?
You're absolutely spot on. I think during the working group, there was a lot of discussion that the data or the data collected in terms of velocity data are very Europe-centric. But working group 145 actually has got a fair distribution of Japanese port and Europe ports. Now with working group 211, we correlated the findings of velocities. We did use a couple of ports in the Western region in Australia to pick up data from there, because Western Australia is quite exposed. The birds are quite exposed out there, and very often there's a lot of higher than design velocities for vessels. So some of that data was fed into 211 numbers just to make sure that we've got the right ballpark. Now, in terms of data collection, that's a change. I think I'm hoping the Australian industry to pick up. Now, there's a lot of modern vessels that has got velocity recording capabilities. I think it's a matter of the port authorities better engaging with stevedores and with vessel operators to sort of get this data, because it can help a lot with the design. So there's also a lot of new products since the development of these guidelines in terms of cheaper ways to sort of get data and store it in a cloud space. So whenever required, you actually just with a click of a button and log in an account and you get all that data. Now that can save a lot of money in terms of designing Fender systems. As we are aware, a marine structure can live up between 50 to 100 years, but a Fender lives only up to 20 or 25 years, depending on how it's used. So we know that every berth is going to be subjected to 1 or 2 changes of fenders. And I think it's critical that the next assess that we had a question just now about existing berth, the next assessment that we do, we need to sort of use 211, but we need to use it with reliable data, site data, that will give us an idea if we have over design or under design. Obviously, we are going to be limited to a template of fixing the fenders. So that's some of the criteria we have to do. But yes, I totally agree with you. I speak to every port authority and tell them, collect data, please invest some money in that, because it's the future. Yep.
I'll limit this for one question, this question.
For permanently moored vessels, does the new standard require us to do a DMA every time? And then once you have those results in, how do you actually go about, I guess, using those different frequencies and berthing energies to look at the fender selection?
Yeah. So a DMA is only required when you've got a lean on load. So that would mean if you've got a vessel that's berthed for prolonged periods of time at the berth. Now I'm dealing with one project where we've got a vessel that sits there for 3 months without getting out. And obviously it just gets out when the weather is bad, just for safety reasons. But that in my experience, that is probably a typical example where DMA is required. But you can also get away with a static boring analysis just to understand what the pressures are within the fender. And my rule of thumb, not the guidelines, if you find something less than 25% compressed, you should be fine. Once it starts getting above the 25%, when the reaction peaks up, then you need to do something about it.
We will have some more time during the tea break or during network session where you can ask questions, even panel discussion towards the end. That may be the time. Thanks, Harvinder, once again.
Pleasure. Yeah.
Before I call upon our next speaker, I would like to thank our sponsors for today's event, Jacobs and Trelleborg. We have Adam and James and Rohan from Trelleborg. So if you have any questions, you can ask them. And also we have, Chris. Yeah. We also have Athol, Seren, Harvinder, myself, and Ng from Jacobs. If you want to know more on what we do, you can talk to us. So the next session is, let me open my. Is on asset owner focus. So Sam Mazaheri is going to present this session for us. Sam is a chartered engineer in civil, structural, and asset management disciplines with over 30 years of experience in the design, assessment and maintenance of maritime and port infrastructure. As a principal engineer at Dalrymple Bay Terminal, he is responsible for the engineering performance and resilience of one of Australia's most critical bulk export facilities. He currently serves as the Queensland and Northern Territory Chair of PIANC AUNZ and contributes to several national and international technical working groups, including PIANC WG211 on Fender systems. His applied research spans climate impact assessments, infrastructure resilience, and digital twin technologies with recent involvement in the Smart Crete CRC initiative. And this session will focus on the practical fit for purpose engineering and innovation. Sam brings deep insights into Fender system design and performance, supporting the delivery of sustainable, safe, and long life port infrastructure. Can I call upon Sam to do the presentation for us? Thank you.
Just put Harvinder name and, just replace me with Jacobs.
My apologies. Yeah.
That's good.
Yeah. There you go.
Okay,
Use
thank
this
you.
if you want,
Yes, let's see if I can,
Yeah. Okay, yeah.
stay here. Otherwise, I will
Sure,
pick that
sure,
mic. Yeah, thank you very much. It's very difficult to talk after, what, Harvinder mentioned in terms of the design and risk and, went through all of the details. So I'm trying to look at in a different angle and just, just via operator's lens and see, okay, how the guidelines looks like from Port Authority and how, what sort of questions they try to ask and how they are going to adopt it. Since the publication, I guess I was, aware of what's going on within that technical group and some presentation, before the publication, Harvinder provided, and we also realized that the measurement of the approach velocity and the collation of the vessel data, which was extensive, and that was additional guidelines published prior to the publication of WG211, how that's going to impact in terms of the asset owner, in terms of how we are going to comply with the new standards and what's going to happen with the fenders designed, for example, 40-45 years ago. Harvinder mentioned that the history 1984, then 2002, and then 2024 we have a transition. Going to be 2026 probably. That's going to be the final date for the publication, and then what's going to happen in the future. So most of the ports design in Australia, it was in 1970s, 1980s. Even it was before the first publication of the PIANC guidelines. So they have done based on whatever experience they had, and still working on with that sort of design. Yeah, this is the middle, but it's just working with your hands. That's yeah, that's okay. So is it working or?
Yeah, it should be okay now.
Yeah, okay, yeah. Let's see. Okay, it needs your hand. So it's working now. Okay, that's the new guidelines. Probably you have seen it or downloaded if you're a member of the PIANC, or have read through. From my understanding, I try to put it as a nutshell. What's the when I get to the introduction, I'm not getting to the details what Harvinder mentioned, but from if I wanted to present to the stakeholders or the board of the port operators, I'm not going to go to the details or present the technical and the formula. They don't understand. They don't have time. They wanted something in a nutshell. So if I wanted to tell these guys what's between the WG33 and WG211 from, my understanding, we got a fixed velocities, limited input as a nutshell. What happened in WG211? Site-specific respects. This is what, Harvinder went through the details. Required pilot input and also berthing lock. So that gets to the question that, Richard asked recently, do we have that sort of information for the Australian ports? And for the existing, this is one of the issues. For the future development, you don't have any pilot, you don't have a log, you want to design it from the scratch, how we are going to, carry on that input into the new design. And also, as Harvinder mentioned, is not an update of WG33. I was asked by, the asset owners and the investors several times, what does it mean? They just reshuffled the guidelines and just develop a new one? Because this is how when you read the introduction, this is how, being interpreted. This is a new guideline. So you have to start it from the scratch. It's not an update. You say, okay, we followed that one, that section being developed precisely, or that parameters now is in a more precise, value, and you can select it in a better way than we used to select it in the past. So these are some sort of questions when you start reading the guidelines. And I was asked that sort of question several times. The key changes, okay, this is overhaul, which creates a lot of issue. What does it mean in terms of, asset management? Overhaul, how in terms of the safety and insurance you're going to interpret? If you just provide that one to the insurance company, how they are going to, translate it from their own lens. Site-specific data, I was asked, okay, that site-specific data, if you start from now, how long data you need to, to say that, okay, that site-specific data going to be sufficient for changing from the previous guidelines to the new one. Assume that you say, okay, this is the new guideline, I'm starting to record data, environmental data, and also approach velocity, pilot log, everything. And then even because in the past we got a lot of paper format data, and then how we are going to transfer that one into the digital. That's, a lot of issues. And design safety. I guess this is one of the things we are developing at the moment, and this is one of the center of the attention from the port perspective. The safety is the core of whatever we do. So we pay a lot of attention in terms of the safety. I will go through that one a little bit at a later time, because the way that, the current design compared to the, the previous design compared to the new guidelines and the design, in some cases, we have considered, over design items. So in terms of the safety, do we need to change it? In terms of, you have already spent it, the infrastructure, all of the connections and the details are based on the size of the fender that been designed 40 years ago. And assume that in one of the scenarios, you are reassessing the fender, and the size of the fender, now is more optimized. You can just downgrade it one size or two size, or change the type of the fender. So is it worthy to go and change the infrastructure and the connection and everything in order to accommodate for the new fender, or you just keep using the existing arrangement, even it's going to cost you in terms of the fender more than what you needed? So there are so many questions, need to be, answered. And I haven't seen, from my lens, anybody from the very large ports, they started to change the design or the fender according to the WG211. It's pretty new, but, we want to see how does it land. In terms of the details, this is how I categorize it. The approach is site-specific respace, which is okay. Input assumptions, variable vessels, berthing speed, and and angles I have some issues because in Australia, the environment that we are facing, particularly in the eastern side, Queensland, and also, New South Wales, we are quite different, comparing to rest of the world. And we got a lot of open ports in Queensland, and they are not protected by the breakwater. And, we are prone to the swell, sea, climate change, wind, everything. And as Harvinder mentioned, that WG211 is not covering the moored vessels. And we have a moored vessels with a lot of swell and variation during the berthing time, because in most of the cases, they are going to be alongside of the berth for 24 hours, 36 hours, based on the loading rate and also type of the vessel. So these are, we have some issues in terms of, getting the right data. In terms of the design flexibility, it's adopts local conditions if we have that conditions, which is good. A stakeholder involvement, I guess this is very, very, massive improvement. Deep operator involvement is essential and is a must. And from my understanding, even for the new wharfs that you're going to design, you need to start communicating with the operator in the first place, which is good. You are just bringing the stakeholders into the design phase, not to do the design and handover and commission to the operator. They come back with different type of, requirement. Risk consideration is the focal point to the design process, which is, I guess, we are using risk for every type of the asset that we are managing right now. And multiple contact scenarios is, specifically addressed, and the focus is broader performance and safety. So as I mentioned, from the implications for asset owners, operators must provide berthing data. It says not optional, and this is one of the things that we struggle. New standards for inspection, reliability, and failure definition, which is okay. This is the collaboration with the manufacturer as well, because, this is what, from time to time over the last 40 years, we always adopt ourselves with the development of the inspection plan provided by the manufacturer. And these are the equipment we always follow the inspection plan, from the manufacturer. Failure can occur without visible damage. This is quite, because we are talking about the rubber stuff. And from my understanding, from structural engineering point of view, the role of the fender is receive the force from the vessel, reduce it, and react it in a lower load. Then you have the structure, whatsoever structure behind of that to carry that load. The point is that transfer of the load is not consistent, because we are not talking about a consistent behaved material. That behavior is going to change from time to time, particularly when your fender is exposed to the very high UV situation and in a very heated or moisture condition, which, most of the North Queensland ports are in that condition. So it's very difficult to predict, okay, what's the performance going to be? And that's the reason we do the hardness testing more regularly. And when the hardness, even the hardness test is just on a middle circumferences of the cone shape, and it doesn't represent the whole system, but we are trying to, accommodate the results in a way that when we need to change it, and the fender is not performing in a way that should be. Maintenance, because you designed, we have a design, you put it there in terms of the, when we are in operation, the maintenance and the whole of life is a critical component of the asset management. So in terms of the WG211, in terms of the inspection and maintenance, it has a very detailed table 11, PIANC-1, which is risk-based inspection frequency. And based on that risk, you can change the inspection frequency, and it is tailored to fender type, location, criticality, which is, a huge, I guess, upgrade to what we saw in WG33. In terms of the whole of life, the degradation over time, like, rubber fatigue, corrosion, UV impact wear has been considered, but this is how the manufacturer is just taking also on board in order to accommodate the new parameters into their catalog and also into the inspection plan. In terms of the accessibility, we have always, challenging when we want to access the asset and the equipment. And, Fender is one of them. When you have a very large Fender sometimes, and it is, you have a very large tidal situation, which we have, 6 meter, and it's just fluctuating, and the Fender frame is pretty large as well, then you need to inspect it. So always, accessibility is a challenge, an issue. And also in some cases, you need a rope access, you need to get into the confined space, criteria, you need the qualification and train people to do the job. In terms of emerging technologies, address, drones, sensors, 3D scanning. It's just, I guess, broadly just addressing, we don't have the details, okay, how the drone inspection gonna help, for example, in terms of the hardness assessment. Can we do it? Do we have any sensors to adopt to drone? And then you do the hardness testing. For other parts, you have some criteria for getting to the proximity of the structure when you're operating drones. So the question is going to be, when you have a corrosion on a bolt, on a nut, on a cleat, on a connection, how the drone inspection going to give you the details that you wanted. And you want to make sure that every single component of the fender is fit for purpose, because the fender is not only the rubber cone, which is the rubber cone, for sure is the main core of the fender, but the front frame, the chain, the nuts, all pieces, they should work together. And if one of them, goes wrong, that might, end up to other, failure and, issues with the fender. And also in some cases, because we have so many uncertainties when a vessel is approaching, even we are saying that this is a controlled approach with the, tug assisted, but in some cases, I have seen incident reports that, the vessel hit outside of the, designed or instructed approach angle, or the velocity was over the allowable velocity. And I have seen the damage in the fender or in some of the rubber frame in front, and nobody expected. But the point is that you need to get there and resolve the issue. And then in terms of the condition data, how that condition data and new guidelines gonna fed into CMMS and digital register. This is one of the issues. A lot of asset owners, they have converted to that sort of asset management. Now a new guidelines and a new requirement needs to also fit into the new system, and how this going to be aligned with ISO 55000, which in general, in terms of the life cycle management, it has the alignment, but practically speaking, how you're going to make it into that system, we need to work on it. Some hidden risk is still there, because we are still relying on a lot of visual checks. So if the visual checks are not good enough, or the people who are doing that visual assessment, they are not experienced enough what's going to happen in terms of the risk, because it's in some cases we are struggling to find very qualified expertise to do the visual assessment. And even in some cases, I have seen we are using for the very detailed assessment, using some some gadgets, but the point is that how we are using that from one team to other team, from one personnel to other personnel is going to be different. The results are not the same. And I call this one hidden risk. And in terms of the asset management, how we are going to address that, hidden risk when you are, you wanted to perform for a longer time. And also some highlights for the need for non-destructive and invasive inspection, which might, alter the operation of the wharf as well, because it's not only one fender you're taking out. If you're, accommodating large vessels, which requires multiple fender, if you're taking one of them out, it means that the whole, berth is out of operation. Operational lessons, examples, poor berthing data, inaccurate, this is one of the things. Deferred maintenance in some of the cases, berth shutdowns or specs mismatches, some contractor issues. There are some of the things, in the practice we will see it. It's nothing wrong with the guidelines. These are, we have those kind of issues with every standards and every sort of, alignment with the guidelines and, standards. Operator's role. I guess this is probably important, and I try to take that part seriously, because if that's going to be implemented 100%, it means that the port operators, they need to start collecting the data. So it means that they have to change the way that they used to collect data and align themselves into that guidelines for collecting the data, including the berthing data, and try to analyze the data and provide the feedback. So it means that it's like timeline assessment as we move on from now. Documentation, I guess Harvinder mentioned that. I guess in every engineering aspect and asset management, documentation from my experience is more than 50% of the whole issue. If you don't have a good documentation, you don't know what happened in the history, so you are still trying to assume how you are going to resolve it. But if you have a good documentation, then you can analyze the data and then see what was the trend in the past, and at least you follow the trend and put additional assumptions for the future trend. So it gives you a better outlook for the future. And the most important part, and it was highlighted in the guidelines as well, PIANC guidelines is, PIANC itself is not a certified association. They are not certifying. They provide the guidelines, and they ask third parties who are accredited based on the, the location or the nation to follow the guidelines and provide certification. And certification is very important. And I will go through the certification in my next slide, which is here. So these are the certification required, and it's part, and it's very important. And I believe Harvinder address and touch a few of them. The material certification that comes from the manufacturer, this is very important. And also as a port operation and authority, we need to go through it and check it, one by one. We do it for every other facility as well. Factory production control, this is going to be against ISO 9001, and probably, the guys from Trelleborg, you're going to probably, provide more details at a later time. Type testing certifications, which is, performance, reaction force, energy, absorption angles, with all of the details provided earlier. I guess this is very important. And also that test should be witnessed by independent, body. This is very important. It's not just providing the report by one of the labs. It's one accredited third party, they need to be there as well. And also project specific performance, that should be under site specific condition and risk. And I guess this is very important to understand the condition of a specific site that the fender going to be installed there. Full scale or prototype testing, I'm not sure whether, we have done it, because this is pretty expensive. It's not, in terms of the wording, it's very easy. You can just write it down. It's like, when I was in a maritime design long time ago, it was, when the physical models and, all of the flumes across the world, we got, the big one, the commercial one, and, everybody was saying, okay, why we don't put a full scale of the breakwater that we want to design? And I said, okay, how many scenarios do you want to, create a physical model and, test everything? It's pretty, cost prohibitive. So the full scale testing is like, you go and design and install it and you have a berth already and just, have a large vessel to come and, berth alongside and say, okay, I'm going to full test it. What's going to happen? So it's going to happen, it's going to damage the fender, the wharf or the vessel. So that's going to be the consequence. In installation certificate and also, as I mentioned, third party independent verification, cover designs, cross-checking, and testing. I guess these are very important part of the fender. Getting to example, I'm over the time. Now I'm just trying to get to the 5 minutes. Okay, I try to. So this is one of the examples. I wanted to use the WG211 and go through the fender design 25 years ago. So this is the fender design. This is one of the, you can see this is the plan. That's the size of the fender. And also this is a cross section. So you can see that fender is in the face for the, for accommodating more than 220,000 ton DWT vessels. So it's pretty large fender, and we have several of that. Is in open water in the water depth of 17.5 meter LAT, and is exposed to swell, sea, waves, cyclones, high winds, whatever you want to name it. And these are the design parameters used back then, because I'm going to use that one and compare with WG211 and see how these, how the design parameters are now standing against the new design guidelines. So you can see the berthing angle 3 degrees, maximum design reaction is 3,350 kilonewton, if I can read it from here, and berthing velocity 195 millimeter per second. Is just less than 0.2 meter per second. And it's quite, obviously I've done it based on WG33, yeah? Harvinder, is that correct? They just use the parameters provided by that guideline, because that was designed in 2000, I believe 7, probably less, around 20 years ago. That was part of the expansion of the Dalrymple Bay terminal. So this is the important part. I tried to use different CE and also different type of the vessel, and the dashed line is current design energy, 295 kilojoule, because this is based on the kilojoule. This is not based on the kilonewton. And you see the other lines, how the other lines are developing for the small vessels. I guess we don't have any issues. You can see all of these, the orangey red type graph. They are sitting far below the design berthing energy. But when you get to the larger vessels up to 220, you see if we just go beyond the 0.20 meter per second, you just get over 30,000 kilojoule. Otherwise, it means that the design was conservative back then, 40 years ago. So in terms, when you compare that one, they say, okay, in terms of the safety, we haven't compromised the safety. So we use a larger size of the fender rather than, the less required. So let's get to the next graph. I'm just trying to use all of the parameters and assume that the design reaction force versus berthing velocity sits at 70% relationship. And this is an assumption. So this is based on, the data and what, how we want to use it. So it means that if I wanted to use the same berthing velocity used back then, I'm not saying that berthing velocity is accurate. It was an assumption. We have the data, and if we, analyze the data, probably we come up with a different berthing velocity. And the point is that we are in open water. Then the question going to be, okay, what's the likelihood that the tugs, the assisted tugs, they are not going to follow with the berthing velocity, and that likelihood needs to go to the different risk, assessment, and then come back to the selection of the berthing velocity. So if you look at this one, and we are going to use that assumption, it means that 1,322 kilonewton. That's how you get it from the new guidelines. What we have used for the designs was 3,300 kilonewton, almost more than double. So it means that considering the guideline, the WG211, which it was pretty interesting for me when I did that calculation and did all of these, put all of the bits and pieces together. I said, okay, probably we could, half the fender size if this is correct. Manufacturer data report, I just passed that one because probably I'm over the time. Inspection and test plan, I just pull that data from what we already do there, and I leave that one to Trelleborg team to go through it in more detail. My key takeaway going to be, okay, we need to work together more closely because it's still a lot of gray area. It's not straightforward. It's not like that, okay, you hand over the WG211 and assume that it has been finalized. This is the next 2 years. We are getting back together and say, okay, this is the guidelines, just use the guidelines. It's probably going to be a little bit difficulty, and we need to clarify more particularly for the existing terminals. It's a lot of challenge, and I believe this is the way, and within the PIANC, we can use our site specific and our port conditions into the guideline more. And this is what I'm trying to recommend. Just bring more port operators into the collaboration of the guidelines for the future. We have the manufacturer, which is pretty good, but we need to bring the port operator, because port operator is one of the key important factors highlighted by the guidelines. So if we want to have their contribution, let's bring them during the development and finalizing of the document, not providing the document, handing over to them and say, okay, go and implement it. That's my key takeaway. Thank you.
Thank you, Sam. It wouldn't be fair if your allocated 30 minutes is not given to you, but you got the 30 minutes. However, we encroached like 15 minutes into our tea break. So I'm hoping 15 minutes is okay. We'll be back again around 3:15 for the session 4 and the panel discussion. Before we break for the tea, I would like to thank Engineers Australia for providing this venue and also the audiovisual equipment for us for this afternoon workshop. Tea break. Thank you. So welcome back. We will have a couple of sessions post tea break. You can bring your food and drinks. Right. If you have not had a chance to sign in yet, please, if you could use this QR code to sign in. Yeah, the bit.ly may be showing up some advertisement at the top, but there would be a button at the bottom, continue with the destination. So please click on that and move to the actual sign-in form. So I have some additional papers here with the QR code on the mid-row tables. Please use, and I see about 1/3 are missing. Some of them are now signed in. Still 5 to 6 more people need to be signing in, please. So I won't take much time. So we are now on session 4. This session is on, so James and Adam are going to speak in terms of this, what WG211 is from manufacturer lens. James is a mechanical engineer with 15 years of experience, spanning machine design, manufacturing, project management, and team leadership. For the past decade, he has planned, engineered, and delivered complex marine fender systems across the Asia-Pacific region, all at Trelleborg Marine and Infrastructure, where he oversees project and sales offices in Sydney, Singapore, Japan, and China. Adam is also a mechanical engineer who oversees all sales, engineering, and project management functions for the fendering projects across Australia, New Zealand, and Oceania. Originally from the USA, Adam has been involved in hundreds of marine fender projects across the North American and Australian regions, and his extensive background spans sales, engineering, project management, design, and manufacturing within the marine, consulting, and oil and gas sectors. So this session delves into the manufacturer's side of fender systems, guided by PIANC Working Group 211. Participants will learn about the interface between engineering design and manufacturing, covering essential information like drawings and specifications. So this session also examines the production methods for different fender types, including rubber, steel panels, and pneumatic or foam fenders. The discussion will include key testing procedures, factors affecting results, sustainability, and how to specify performance and durability requirements. So without any delay, I understand this is being shared by both James and Adam. James will be presenting the first half and then Adam's. So I call upon James to present for us. Thank you. Oh, so I'll have to.
This hasn't gone well for everyone else. So.
Let me see. Let's try that. Mid button.
Click the
We'll
in
click
the middle.
here, and then. Yeah.
Beautiful. All right.
Yeah. There you go.
Thank you, Harry, for the introduction. Just quickly, thank you very much to PIANC for inviting us here and giving us the opportunity to sponsor this event. Trelleborg has been involved in PIANC for many years as an active participant and platinum sponsor. We're very happy to be here. I want to say thank you to Sam and Harvinder as well for their presentations. And yeah, I think it's just a great opportunity for us to share our perspective on Working Group 211 and Fender designs and the latest developments and improvements from Working Group 33. So as Harry mentioned, I'll be sharing and co-presenting with Adam Sellers, who's the General Manager for the Australian Projects and Sales Office. I'm the regional director for marine fenders in APAC. So we have an office in Sydney, Singapore, China, and Japan. And then we're supported by a number of different services across the globe. So I'll be talking about briefly Trelleborg. We're talking about the interface between the designer and manufacturer, site data and emerging technologies, before passing on to Adam, who'll be talking about the manufacture of fender systems, the testing of fender systems, and the installation, operation, and maintenance of fenders, and then finally sustainability. If there's any questions, feel free to sort of shout out mid-presentation. I may not be able to answer them all, but I can certainly defer to the others. So just quickly, a few slides on Trelleborg. Trelleborg is a polymer company. They make rubber products across every industry imaginable. There's a large number of business areas. The marine group is just one of those. It was founded in 1904 in the town Trelleborg, Sweden. We currently do around 3 billion in annual sales. It's about 16,000 employees globally across 40 countries with 100 manufacturing sites. So it's a big business, but we're one cog within that business. So the business that deals with maritime is Trelleborg Marine and Infrastructure. And then within Trelleborg Marine and Infrastructure, we have several product areas. There's marine systems, there's gas transfer, navigation and piloting, marine construction and infrastructure. And I think the business that most of you would be used to dealing with is marine systems, which consists of the marine fenders business. And the marine fender business supplies any fender imaginable. Certainly all the fenders that are talked about in Working Group 211 and then more. We have cone fenders, cell fenders, arch fenders, unit type fenders or leg fenders, as well as small fenders like extruded fenders, tug fenders. They come under the fixed fender category. And then we also supply floating fenders, which is a side-loaded fender which has a different load profile, which is explained in Working Group 211, Chapter 2. And that consists of pneumatic fenders, foam fenders, hydropneumatic fenders, and donut fenders. It's certainly horses for courses in terms of what fender you use for what application. They have distinct advantages and disadvantages. Some are very well suited for some applications, others not at all. I think Working Group does go a long way in giving an overview of what type of fender is suitable for a specific application, but I'd certainly encourage you to engage with manufacturers early on in the design cycle to get advice on the different types of fenders that are out there and what may be the best unit for your given application. The other part of marine systems is the docking and mooring business, and we have Christoph Kolf here, is the regional sales manager for that business. If you have any mooring needs or docking needs, then he's the man to talk to. Within the docking and mooring business, we have the line monitoring systems or LMS systems consisting of traditional bollards and then quick release hooks. And there's a number of different products within that range. We also have docking and mooring systems as well, which I will touch on. And those systems are very much related to site-specific data and data capture as well. The other product group within docking and mooring is automated mooring systems, which consist of a dynamo unit, which is essentially a bollard or a hook on a hydraulic cylinder, which provides dynamic or dampening on mooring lines, specifically designed for the issues associated with long period waves at certain berths. And then we have the advanced automatic mooring unit, such as the Automoor units, and there's a number of different variations of them, which is newer. I say newer technology. I think it's been around for maybe 10 plus years, but it's gone through a number of different iterations and developments, and it's slowly becoming more and more adopted within the industry, which is fantastic to see. In terms of our global footprint, we've got offices all around the world, as I mentioned, but the key standout items here are we have a manufacturing facility in Qingdao, China. The marine fenders business is supported by a design office in Ahmedabad, India. And we are opening up a new manufacturing facility in Ho Chi Minh, Vietnam, which comes online in November 2025, which we're very excited about. So in terms of the interface between designer and manufacturer, we've already heard a bit from Sam about that, a bit from Harvinder. I'm also going to touch on it and how we see it as a manufacturer. So as a manufacturer, particularly in Australia, we've always promoted a whole system approach. That's how we approach it, or brand it, I guess, which promotes cost over life of fender systems as opposed to cost up front. And that consists of design engineering or applications engineering, which assesses birthing conditions, your abnormal and normal birthing energy, which is obviously from Working Group 33, your fender selection, your fender specification, your detailed engineering, which looks at making sure that you're designing your components correctly to the relevant standards, making sure that designs and drawings are submitted to a particular standard, manufacturing quality control, so showing that what you designed and specified and drew up actually is manufactured and supplied at the end of the day, because there's no point in putting all this effort into design, looking at all these safety factors, quantifying everything like that, and then going and manufacturing a fender that doesn't actually meet those performances. So that's very, very important. And then finally, operation and maintenance. You know, once the fenders are supplied and installed, that's just one part of it. They then need to be maintained. And then I think from my experience and our experience, you see a very large range of maintenance activities from owners and asset managers across the world. Some are fantastic, some do very little and just hold on as long as they can. Obviously, the former is much preferred and is going to yield much better returns from an asset lifecycle perspective. Moving on to Working Group 211. So it very much follows this whole system approach. It logically walks through the steps that we go through when we design and supply and inspect or maintain fender systems. Chapters 1 to 7 cover design engineering or applications engineering, a lot of what Harvinder went through. The chapter 8 goes through detailed fender system design, all the different components designs, which is new in Working Group 30, the 211. Chapters 9 and 10 covers fender production and quality control, which is a completely new addition, which is very, very welcome from a manufacturer's perspective. Previously, that very much relied on the manufacturers to educate industry or consultants to educate industry on the importance of that particular stage of the fender life. Now that it's written into an actual guideline endorsed by PIANC, I think it makes it a lot easier to share that knowledge and just raise the bar of the industry as a whole. Same goes for references in terms of installation, operation and maintenance, and then sustainability and recycling, which is chapters 11 and 12. And then chapter 13, the specification spans, obviously, the entire process, chapters 1 to 12, and I'll be talking on that a little bit later. In terms of the design and manufacturer interface, it's interesting to hear Harvinder's views, Sam's views. Here's our views, I guess, or my views, and based on my experience. And again, like maintenance of units, scope of work of the end user, the designer, the contractor, and the manufacturer varies significantly from project to project, depending on what type of project it is, whether it's a brownfield replacement like for like, or whether it's a major upgrade or a greenfield project. You're going to see the different involvement of different stakeholders change, but a lot of them do follow a similar pattern, which very much matches what Harvinder explained. One thing I wanted to comment here was the fender management consists through the entire process. Obviously, there's some areas where they can provide a high level advice, but then later areas as you move down the chapters and down the process, they should be getting more and more involved. Finally, I just want to emphasize basis of design, which I'll talk about a little bit more, and then the importance of basis of design specification, which are critical for ensuring that you are designing and receiving economic and durable fender systems. So in terms of the Working Group 211 structure, I would encapsulate all of this as the designer engineer's responsibility in collaboration with the asset owner and operator. So obviously looking at the initial concept, gathering input from operators, terminals, vessel, master pilots, linesmen, etc. They're reviewing the relevant codes and standards. They are then also putting inputs in collaboration with asset owners and operators on sustainability and installation. And they're looking at all the local environments, berthing conditions, etc., to put together a basis of design at the starting point. As we move down, we then look at the berthing energy with the related factors. And I think here the manufacturer can have an input on that. As the manufacturers are specialized in fendering, we obviously do a lot of those projects and have seen a lot of those projects across the world. So we can often refer to other berths around the world and apply lessons learned or best practices from our experience there. So I certainly encourage you involving manufacturers at that point. When you start to get into the fender selection, fender systems design, the design engineer would typically provide a reference design. They would specify the design energy and the allowable reaction force from the structural design. Then it should be the manufacturer's responsibility to go ahead and propose a design that meets those requirements and provide a submittal for the design engineer to then review and approve. Then as you move down to the final stages, the design of the fender system components, the manufacturer, obviously, and the testing, that's very much the manufacturer's responsibility, but the design engineer should be reviewing and approving based on the specification and basis of design, and the end user should also is encouraged to be involved in that. They would typically engage a designer or a consultant to do that on their behalf, depending on the type of project. Finally, the end user is involved in the operation, installation, inspection, and maintenance. I might have to breeze through this very quickly, but I did have a look at Chapter 4 in a little bit more detail. So Chapter 4 details the basis of design, and it outlines the parameters that need to be taken in consideration during for the design of a fender system. It's essentially a roadmap for the design process or a template for developing the document. And fenders should be designed considering the functional requirements, the operational requirements, site conditions, design criteria, return period design life, operation maintenance, and the assessment of acceptable reliability levels. All this information should be provided early on in the design phase, so that designers can provide, or manufacturers can provide input there is an iterative process as mentioned several times throughout Working Group 211. May skip through this because we're short on time. I think the big thing here, because a lot of this is sort of pretty standard under Working Group 211, as has been mentioned several times, a 50-year return period has been used for berthing energy in Working Group 211. 20-year design life is the typical expected design life for fender systems. I think what's definitely new in Working Group 211 is the consequence class, and that feeds back into a number of different elements of the design process, specifically the partial energy factor, the potential safety factor for single and multiple fender contact, the partial load factor of fender system and accessory design. There's also a comment there about the consequence class being selected by the asset owner, which is good to see, the sort of emphasis on the responsibility of the asset owner to work in collaboration with the consultants to come up and quantify what that should be. Working Group 211 says that typically fender systems will be asset class A or B. I think having some conversations with people, the conversations around the economic loss of damage is a topic of discussion that may push you further down that list, but I think A and B is probably the most common area that we'll see. Specifically about Chapter 4 and basis of design, the impact on the industry of this change, as I mentioned, the functional, operational, and site conditions, they're already common business practices. But this Working Group 211 reinforces their importance. The design criteria, the codes, the design life, things that haven't been emphasized as much in the past, so that's certainly well welcomed. And the reliability requirement is completely new, and is that risk-based approach to fender design. From our perspective, I think it's great to see this improved emphasis on the importance of providing the right amount of information early on in the design process. You see, again, a number of different jobs which have sometimes very little information. You're going to get, the quality of information is going to directly correlate to how effective and accurate your fender design is and the asset that you get at the end of the day. The worse the information, the more likely you are to get a fender system that is over-designed or under-designed and may not be fit for purpose. It underlies the importance of maintenance to achieve design life, which is great, and it emphasizes the importance of end-user involvement, which is also very, very important. In terms of specification writing, Harvinder's already said this, so I won't spend too long, but I see the first section here, which clearly sort of delineates roles and responsibilities between the purchaser and the supplier. But the first section I would consider to be put into the basis of design document, the general port and key information, the water levels, the fender system selection, which is not always done, varies from project to project. Sometimes, again, the design energy and the maximum reaction provided as a reference design, and the fender manufacturer will go ahead and propose a selection. But all of this information would be in the basis of design document, which should be provided earlier on in the project lifecycle. As you move through, you start to talk about manufacturing and quality requirements, testing requirements. This should all be put in the specification, which should be issued during the tender, either to the contractor or directly to the fender manufacturer. If you're talking about a design and construct contract with contractors, it's important to have a robust specification earlier on. Without a robust specification, it definitely opens up a lot of areas for interpretation from the contractor's perspective, which might mean that the end user, the asset owner, doesn't get the product that they actually want. Going into the actual details of Chapter 13, we have the 5 sections, which is general information, which is all about what the fender manufacturer should be supplying in terms of their compliance with Working Group 33, type approval, ISO 9001, the basis of design, manufacturing and testing quality requirements, delivery and installation and storage, and sustainability. And just want to highlight here that verification is essential. So testing requirements, ensuring that what is designed for and specified is manufactured and supplied. And then finally, a strong specification means reduced cost over life of the fender, lower OPEX through an increased service life, and also lower maintenance. Designing for maintenance is always important. Increased port efficiency and safety, and reduced liability for all stakeholders. Now, I'm going to spend the next 7 minutes, so Adam has some time to present as well, talking about Working Group 211 and emerging technology. So we've heard through all the commentary so far that site-specific data is very important under Working Group 211, especially ensuring that you're not over-designing your fender system. So it's mentioned in Chapter 1, the introduction, where literally says Working Group 211 strongly recommends the use of site information. If local knowledge is ignored, fenders might be over-designed. Chapter 5, berthing energy, is where you start to see the impacts of site information, which I'll talk about, and Harvinder's already talked about. But it will allow for lower partial energy factors, as well as the ability to use a statistical approach to berthing velocity, which can also have a significant impact on your fender size as well. And then finally, it's mentioned in the installation, inspection, and maintenance section under emerging technology. So where does site data have the biggest impact? As Harvinder mentioned, the berthing velocity factor obviously is the biggest component, being the squared component of your design energy or your characteristic berthing energy. If you don't have site data, you are limited to table 5.3, which can be conservative, as we discussed. If you do have local knowledge, then you can take the 0.02% probability of exceeding the berthing velocity per berthing maneuver, which can be significantly less than the conservative values shown in table 5.3. So Working Group 211 says using local knowledge is the essence of this guideline. The velocities presented in section 5.4 5.43 and 5.43 should only be used if local data, information, and experience is lacking. These velocities are considered to be safe and based on a global data set, therefore have a tendency to be conservative. The next area where site data has a big impact is on your partial energy factor. Again, Harvinder just covered this, but just looking at this first example here, if you have a look at table 5.8 for single fender contact in a non-monitored berth, you're looking at a 1.3 factor. If you then move down to a monitored berth where you take out the navigation conditions, you can reduce that by 0.05 to 1.25. On the extreme end, you can ensure you reduce that up to 0.8 by having a monitored berth. So monitored berthing can reduce your potential partial energy energy factor by 4% to up to 31%. 31% is probably very much on the high end, and it is not going to happen a lot because the consequence class D is generally not going to come about. So a more realistic sort of reduction based on some of our high level numbers have been maybe a 14% reduction for jetties and a 4.5% reduction on container terminals. So what is a monitored berth, I guess, is the key question here. PIANC says that another method to control uncertainty in berthing energy is to monitor the berthing velocity, where masters and pilots are aware of realistic berthing speed limits, and when berthing aid systems are used, such as portable pilot units or fixed shore-based docking systems, this is defined as monitored berthing, and lower partial energy factors can be taken into account. So monitored berthing is considered to be piloted berthing with PPU units and or the use of shore-based docking aid systems. A final section where site local data can have an impact is step 8 in the partial energy factor calculation, which is the correlation factor. So working group 145 from a review says that vessel berthing records do not show a strong relationship between vessel size and berthing velocity. So we have a YC factor of 1 here if there is no correlation. If there is a correlation, however, it's possible using that data to have a YC value of less than 1. There is a paper out there, Rubos, Iverson, and Oskamp from 2024, which I do not know the details of, so do not ask me. Maybe ask one of the others. But it found that the YC factor was closer to 0.6 for a container terminal with favorable navigation conditions in Rotterdam. So that's a huge impact from looking at berthing velocities from a local data set. So how do you get that data? Questions been asked, and Trelleborg have a number of products out there in the marine space, and it's something that we've been looking at for several years is data collection, storage, and producing products that can utilize that data. It's certainly a challenge, but we do have a number of products that can do this, both on the vessel side and on the port side. The products that are most relevant are the Safe Pilot PPU units, which marine pilots will bring onto a vessel to aid with berthing, and the Smart Fender and Smart DAS, which are 2 wharf-based products which can provide data. Smart Fender is currently in development, so we're doing some trials at the Port of Moerdijk in the Netherlands, and with Ras Al Khaimah Wharf port in the UAE. It's a wharf-sided mounted system. You can see the box there in blue on the right. It can be battery or mains powered, provides specific fender data by using infrared lasers and distance measurements on the back of the fender panel, as well as a laser that points seaward that picks up on the vessel and can provide short range vessel velocity. So it's more the initial velocity as opposed to the longer approach. Some of the key benefits or use cases is obviously data and related to 211. So that data is stored in the cloud, can be represented in a dashboard, which you can see there. You can also download historical data for your own analysis or have a data feed into your own systems, which you can use to do trend analysis for design and maintenance. or also used to design fender systems under Working Group 211. The other use case is overload warning. So if your fender is overloaded, you know when it happened, where it happened, what time, and by how much, which depending on the different stakeholders involved at different berths can be important information, because you may not actually be able to know when an overload incident occurred and who caused it. The other product is the Smart DAS product, which is a fully developed product, which I'll go into more detail here because of that. But DAS systems or docking aid systems have been used in oil and gas terminals for a long period of time. They're typically hazardous products, and they haven't really been used on continuous key walls or container berths. The Smart DAS is a simplified version of a docking aid system, or a smaller version, I should say, of a docking aid system, which is not completely non-hazardous. I should go back. To make the form factor smaller and make it more applicable for container berths, but it has an infrared laser, and it captures vessel distance, velocity, and longitude angles. So you need at least 2 units. It also has a web application for real-time and historical data. It's also an economic way of doing a berthing aid system because you don't have a big display board. So the traditional DAS system has a big display board which shows the velocity that the pilot and the master can actually see from the bridge of the vessel. This is a web-based app that can be brought up on an iPad by both the pilot, the master, or anyone on the terminal, both from operation side or the asset owner side as well. So the benefits are safe, efficient, and reliable berthing operations, alarm functionality if during your approach, because it has a 200-meter range, you can get an earlier warning or an early alert of berthing speeds or berthing angles being exceeded. That offers the ability to protect your data both through situational awareness and through constant monitoring. It provides data logging and historical records and data insights for design under 211 again. I'm going to move through this quickly and finish up the last 2 slides. Just quickly looking at Working Group 211 and looking at a non-monitored and then a monitored example. So the key factor here is for a container berth, the reference partial energy factor under a monitored berth goes from 1.25 to 1.15. And then when you move down to the bottom, you've selected your fender based on your design performance, that correlates to a 12% reduction in reaction force. And then on a jetty, similarly, you're reducing your partial energy factor from 1.65 to 1.45, which is a 13.8% reduction in reaction force. So again, reinforcing the importance of monitored berthing and local data. There's the 2 case studies for the Smart DAS system, which I'll use to finish up. New South Wales ports we've been undertaking work with them as an R&D project. So they had a number of incidents at one of their berths where a vessel will come in too fast, it would damage the fender and potentially do some damage to the headstock and piles. They weren't aware of that until they did regular maintenance under the wharf, which was 6 months after the incident had occurred. They didn't know which vessel had caused it. So they wanted a system that would match AIS data with berthing data and would give them real-time alerts and knowledge of berthing overloads, and also the data so that they could assess and analyze that. New South Wales ports have a big data analytic, or have a data analytics team, and are pushing the use of data in ports more and more. They used 8 lasers, and they also had an LED display board, so it's a bit of a hybrid system. But that's that project there. Another project was at Phillips 66 Radio Refinery, where the customer wanted a docking aid system, but they didn't have the budget for a full system. So the Smart DAS is a cheaper, more economic version of that without the display board. It also requires less civil works and cabling installation. So they were able to install a docking aid system without the large price tag, I guess. And that's my section. I'm going to pass it on to Adam, who's going to talk about Fender manufacturer and quality control and testing. Thank you.
Thank you very much.
Alrighty, so I'm going to do my best to go through 4 chapters and all the manufacturing processes for fenders in a little over 30 minutes. So I'm going to try to go through this pretty quickly. If you have any questions, feel free to save them for the panel discussion. So chapters 9 and 10 in Working Group 211 cover manufacturing of fender systems and the test procedures. As previously mentioned, this is something that wasn't really covered in 33 at all. So welcome improvement, and hopefully we'll be able to be carried through the industry to elevate standards for these items. Chapter 9, to get into it, starts with qualifications, different aspects of the manufacturing processes, including rubber compounds, the actual processes of how these items are manufactured, including different components of a fender panel system, like the steel panels, UHMW, accessories. It also does cover the pneumatic and foam fenders as well. So it's pretty broad ranging. It is at a high level. So hopefully I'll get into a little bit of detail on some of this stuff today. But the working group report does provide a very good overview and a lot of detail on this kind of stuff if you ever are interested in some going back for reference later. To start with, the first part is the rubber compounds that are actually used in the fender manufacturing. They are made up of anywhere from 15 to 20 different individual ingredients for a single rubber compound, especially for the high quality ones. For reference, you can see the TGA outputs, which I'll go into a little bit later about that testing specifically, but those are Trelleborg's reference TGA values for rubber compound for the high performance fenders like a cone or cell fender. The foundation of these compounds is the actual polymer rubber blend itself. Typically, this would be a blend of a natural and synthetic rubber, so an SBR specifically. The rubber used should be a virgin material rubber and not include any recycled or reclaimed rubber. Like Harvinder mentioned earlier, there's a vulcanization process that goes into manufacturing these fenders. That leads to very long chain polymers with sulfur cross links, and breaking those links is incredibly difficult. It's a very cost, time, and energy intensive process. So it's not practical to actually use recycled rubber. You can significantly harm the performance and durability of the fender, leading to more frequent replacements, more operational expenses, and more cost through the life cycle of the system. Next major component of the compound would be the fillers. Typically, you would look at reinforcing fillers like carbon black. These are used to improve the physical properties of the rubber, in addition to the UV resistance, environmental resistance as well, and the processing of the compound is also helped. Sometimes cheaper non-reinforcing fillers like ash or calcium carbonate can also be used. Minor amounts of these non-reinforcing fillers are okay. As you can see, we have a 6% maximum in ours. However, too much of these can harm the durability and significantly impact the lifespan of the fenders themselves. So definitely want to make sure that you are testing for this and capping that amount, as it can lead to some significant impacts on the performance. In addition to those two main kind of fundamental components, there are a lot of other additives that go into this as well. There are certain oils, processing compounds that are used to help with the mixing. There are also vulcanization accelerators, which would be the sulfur compounds that are used to create those crosslinks during the vulcanization process. And finally, there are antioxidants, anti-ozonants, and other environmental protection compounds that are used and mixed in with the compound. So all these different things are built into what goes into the recipe, if you will. Once you have your recipe, what the actual rubber compound is going to be. You're then going to go through and actually do the manufacturing process. So first step is going to be building the compound and mixing the compound, which is not just, dumping everything into a big vat and stirring it up. There's different steps to this. It's a controlled process to make sure that things are emulsified and actually mixed properly. Next, you get into the actual building of the fender process. So this can go through various processes that would actually be used. Typically, again, for the high performance fenders, you'd be looking at a molding. So if you look at that top left picture there, that is actually one of the compression molds at the Trelleborg factory. So this looks like an SCK fender. The process would entail layering in sheets or blocks of rubber inside of a mold, and then putting it inside of that compression mold, compressing it under heat and pressure to be able to form the final fender dimensions. A key part of this process is preparation of the steel. So that would be that top right picture. There are certain compound preparations that are used to be able to create a strong bond between the steel and the rubber. And then that steel would be prepared and layered with a couple initial layers of rubber before being inserted into the mold and then molded as part of the whole fender body. This preparation is essential, and there is a physical property testing that does cover the bond strength between the rubber and steel. Oftentimes, this is a point that can have a critical stress within the fender body and can be a point of failure if not done correctly. So some fenders can also be constructed through wrapping around a mandrel or extrusion methods. Typically, those would be like cylindrical fenders or other smaller utility type fenders. So those are covered a little bit in 211, but the main focus is going to be on your high performance type fenders. Final process would be the curing and vulcanization process. See that bottom picture, we have one of the vulcanization control setups. It is a very highly controlled process that is both temperature and pressure sensitive. And so that's what actually goes through, uses those sulfur compounds to cross-link all the very long polymer chains. And that's what gives the fender the durability and the performance properties that you would expect out of one of these high-performance fenders. And that's the final process that actually converts the raw, somewhat soft rubber into a usable fender. So each one of these processes has significant impacts in their own ways on the performance and durability of the system. So it's always helpful to have a good understanding of the process to be able to talk about it, understand what those physical property testing, understand what the testing is actually looking for and checking to be able to specify properly. Next, the report goes into the fender panel manufacturing. So as previously mentioned, you want to ensure that workshops that are going to be doing the manufacturing are qualified up to the proper standards. Typically as a minimum, ISO 9001, not mentioned in the report, but ideally you want 14001 as well for the environmental considerations. You want to make sure they have proper welding procedures, clean traceability. You want material controls, proper quality department. ITPs are also a consideration in this section to make sure that clearly defined testing, checks, hold points, all that kind of stuff is defined. Typical fabrication standards, we'd be looking at AS 1554 or AWSD 1.1. A lot of the fabrication for these items does not actually occur in Australia. So a lot of times the international standards like the AWS would be more commonly used where these are actually getting manufactured. Material standards, similar, not typically manufactured in Australia. So ASTM A572 grade 50 or Q355B, which is a Chinese spec grade GB/T, GB&T grade, are the common material standards for the steel construction. Typical kind of construction structure overview for these panels. It would be a hollow box frame. So you'd have, depending on the type of construction or the place of manufacture, you'd have either cross channel or sorry, C channel or T section. Typically, the material costs for the C channel and the overall cost, when you consider welding time and everything, the C channels are more effective for domestic fabrication. There's a little bit less welding involved. T profiles are more beneficial in some areas where you would have higher cost of material relative to labor. You can see a couple, an example down here of fender panel with the front plates off. So you can see that that is a T construction internal sections. Typically, as Harvinder mentioned earlier as well, these are going to be closed box systems. There will be a pressure test done as part of the quality control to make sure that the full internal body of the fender panel is sealed, no water ingress, corrosion protection, to make sure that there won't be any rust or anything that'll start. Speaking of corrosion protection, manufacturing, the painting processes are also very critical to ensure long lifespan of the system. There's a lot of different components that go into preparation of steel when you get into manufacturing processes. So you want to make sure things are going to be clean, they're going to be done properly, you're going to check there's not going to be salts that are going to contaminate the coatings or anything like that. So this can have a very large impact on the quality and longevity of the coating system. So if you want the 20-year design life as per ISO 12944, doing the proper preparation is absolutely critical. And then obviously when you're actually going into the applications, making sure that the environmental conditions are proper, and for quality control checks related to the adhesion testing, holidays, and dry film thickness are important to ensure the quality of the system. Does touch a little bit as well on UHMW PE. Typical manufacturing process for this is going to be a compression molding similar to the rubber fenders. So you're going to get raw material. Typically this would be like a powder that would be built into a mold, compression molded, and then final machined to dimensions for the specific project. Chapter 10 does have detailed properties for the UHMW material as a recommendation. And there are different tests specifically captured in those detailed properties. Generally, we recommend this to be captured in a specification, and it's very, very nicely laid out across chapters 10 and 9 about some of these tests and the ability to just go ahead and include that directly into the spec. So finally, accessories like chains, hardware, and things like that. Most of these processes are typically covered with various international standards. So the report doesn't go too much into specifying how they're made or detailed QA QC processes, as most of the international standards kind of come with that stuff already. But proper QA QC should still definitely be done to make sure that stuff is done right. You're getting the right materials, the right dimensional information, all that kind of stuff on the system. 211 in chapter 9 specifically does also go into the pneumatic and foam fenders as well. So high level, two basic types of pneumatic fenders, one with a chain tire net, one without. Fundamentally though, the manufacturing process across the two is the same. So you get a multi-layer body of the rubber fender for these pneumatic fenders. The outer layer is going to be your abrasion resistant, environmental resistant layer. So this is going to kind of form that outer protective shell. All of these inner and outer rubber layers are vulcanized as well. So similar type of curing process as the molded rubber fenders. In addition, past that outer layer of rubber, you will have a tire cord reinforced rubber layer, which adds strength and wear resistance to the body of the fender, and also helps with the tear resistance and performance under compression. And then finally, an inner rubber layer, which is intended to be the actual air seal and pressure containment layer. So Typically, it is a multi-stage process where these will be laid up. And so it's actually a molded rubber fender as well. You'll typically have two hemispherical ends with sections in the middle. Depending on how long the fender is, these can kind of be adjusted to customize the size a bit. So first step will be laying of that actual outer rubber layer. This is all done manually. You'll have large sheets of rubber where that'll actually be laid in physically in the mold. The molds are on rollers, so you can, as the rubber is being laid, the mold can rotate and you can get the full circumference. The flanges at this stage will also be kind of inserted and laid in into the molds, and the outer layer will be laid up to that. Second main step is going to be additional rubber layers layered in with the tire cord as kind of a composite layer. Tire cords are typically laid at between a 45 to 60 degree angle for strength and durability. And that picture all the way on the right, left, there's a little diagram there where the tire cords are actually laid up and wrapped around the bead ring to ensure that that flange and bead ring is going to be locked in with the rubber body itself. So that's a very critical part of the ISO standard that these are covered by. Typically for the chain tire net ones, the tire cord wrapping is not as critical because the tension is typically handled by the chain tire net, but it's still an important part of the process for the non-tire net ones. Next step is going to be insurance of the adhesion between the layers, so they remove any of the trapped air between those layers and lay up the final inner layer that's going to seal the air inside of the fender body. Finally, in the fourth step, when the mold is closed up, the layers are going to be stitched together at the mold parting areas, which obviously is a very important part due to that being a natural seam, an area where these could fail if not done properly. Once the mold and everything is done, the fender's all layered up, the mold will be pressurized, be checked for leaks, and transferred to a vulcanization process. So again, tightly controlled temperature and pressure inside of these molds. Once the vulcanization is complete, molds cooled, pressure's relieved, you take it out of the mold, and then the chain tire net can be added on at that stage or kept off for shipping, depending on project requirements. ISO 17357 is the international standard that covers pneumatic fenders. So a lot of the stuff in 211 kind of points to this, including the testing requirements. So the testing requirements in that ISO spec are very well defined. Typically, you're going to be doing the same type of fundamental testing, type approval testing, and project-specific testing as you would for other fenders, which I'll get to in just a little bit. You also do your TGA testing to ensure the quality of the rubber compound as well, leakage tests, things like that. So, finally, foam fender manufacturing. So similar to the pneumatics, different types of foam fenders fundamentally all have the same methods of manufacturing. So first step starts with a mandrel core. So there's going to be a steel center of the fender. It's either going to be just a normal pipe with the end fittings on it, or it's going to be a larger section for donut fenders that would go and sleeve on the outside of the pile. Foam comes in large rolls that's staged up to be able to pull off of. You can see in the background there's some different colored foams which indicate the different densities. So depending on the performance requirements, proper foam is chosen, staged, and ready to be layered on. The first step is a winding process we'll go through, and these will be thermolaminated. So there's a torch that will heat up the inner layers as this stuff is getting wrapped. You will wrap the rough dimensions of this foam fender on the mandrel. Once it's wound up, there's a CNC machine saw that will come through, cut it to the actual profile, shape the ends, and bring it to the final internal dimensions for that foam. And then we'll go through a stabilization process for temperature, and you get composite urethane skin would be applied on it after. So this is done with an automated process where a multi-strand winding machine will go through and wrap tire cord while polyurethane is being sprayed on top. So it's an integral composite skin of the fender. So multiple overlapping crossing layers of the tire cord with that polyurethane skin. Typically, as you can see, the top layers would not have the tire cord as kind of a wear layer as it's designed and intended to be. 211 does go through and provide reference performance values for the both elastomer and tire cord that would be used in these types of fenders. So something that was basically completely missing from previous guideline. Finally, we go through the curing process. There's not as much of a vulcanization process that goes through with these fenders, but still curing is required. And then finishing to put the pretty logos and everything on. So next we get to chapter 10, which would be your test procedures for the marine fenders. Major difference in this chapter compared to the previous report is the testing requirements, processes, and recommendations are much, much better defined and clearly stated. There's not the ambiguity that there was in the industry with the last report when we just had that to rely on. Three types of testing are covered in the chapter 10, which would be fundamental testing, type approval testing, and your verification testing. So first off, your fundamental testing. So this is going to be your base testing that is going to be performed by the manufacturer for them to determine their own performance values, their own correction factors for velocity, temperature, and angles, validate the durability test of their compounds and fender geometries, as well as the chemical composition and the physical property validation of their rubber compounds. So again, these are just the ones that are done by the manufacturer for their own data. Once you have that fundamental testing complete, the type approval testing would be the next step. And this is basically all that fundamental testing witnessed and then verified by a third party to then be able to certify that the fenders are type approved in accordance with the PIANC guidelines. Like Sam mentioned, the key part is not by PIANC, but by an independent third party in compliance with the guidelines. So similar type of testing, but very key distinction there. And finally, we get to the verification testing. So this is going to be your actual project specific testing here. There's a few different classes that chapter 10 goes into. First off is going to be the mandatory testing. So these are just the verification of the base performance physical property testing, bare minimum that we should be doing on any project. This is already pretty much the standard in the industry. For really simple, non-critical applications, it's probably okay to get by with this. However, there are some challenges with just doing this testing where you don't really have any kind of external guarantee that the manufacturer's testing is being done properly or they're doing all the testing. You don't have a link for the actual verification of the quality of the rubber compound itself. You have the physical properties, but the actual polymer structure and the compound composition is not contained here. And again, the type approval testing, you don't have the additional validation on that. The next class would be the highly recommended testing, which we absolutely would also stand by as highly recommended tests for just about any project. Basically, these tests, the next level up here includes third-party witness or performance of the testing itself. So commonly known in the industry that, shortcuts can be taken in any industry. So it's part of the reason why we do testing in the first place. So third-party involvement helps ensure that the right testing is being done in the right way. This involvement can be just witnessing the tests at a manufacturer facility. It could also be using a testing jig to capture data, their own data. So like if it was a performance testing, you bring your own load cells and you'd be able to capture the load data during the performance testing. Or finally, the third party can actually perform the test themselves. So performance testing is a little bit tricky. There's only a handful of places in the world that can actually test these fenders because of the unique requirements of a long stroke, and a high load. There's some in Italy, there's 2 in the US, and there's 1 in South Korea. None in Australia or in this side of the world, really. So it does make it a little bit challenging. However, things like the material testing can be pretty easily done. In addition to the third party, for rubber fenders, the TGA analysis would also be added on here. And this would be where you'd test your polymer compositions, reinforcing filler, non-reinforcing filler, all that kind of stuff to guarantee the quality of the compound itself. For foam fenders, they also add on the skin thickness testing and fender pull-through tests to ensure quality build on the foam fenders. So just to go a little bit into TGA testing, this is an optional requirement per 211. However, it is in the highly recommended standard. For those of you who aren't familiar with this test, it's a thermogravimetric analysis. Basically what they do is they take a little sample of the rubber material itself. You only need about 50 grams of it. So this is something that can easily be done from a fender on site. You scrape off a little bit of material, doesn't have to be in one piece or anything like that. Send it to a lab and they basically cook it very controlled temperatures and see at what temperatures different things will burn away. So polymers, oils, certain other additives all have different burning temperatures. And as they measure the weight, as these things burn off, they know what the composition of the quality, the compound is. So very easy test to do, can be done pretty easily, I think, in Australia as well. Very easy way to be able to ensure the quality of the fender compound. And then finally, you get to the optional test, last class here. So these are ones that are going to be considered for more critical applications. The specific ones that are mentioned in the report are going to be your verification of correction factors. So additional tests to verify temperature, velocity, and angular correction factors. Your durability testing. So if you're in a scenario where you've got a permanently moored vessel or a long-term moored vessel, high cyclic loading conditions, or you just want to ensure that the fender is going to be good for 5,000 compressions over the life cycle of 20 years, durability test would be something that would be able to be done. Now, going to the next slide a little bit more on that one. And then the shear compression test, where you do a combined shear and compression, is also an option if you're in certain scenarios where there's a lot of shear loading combined on the fender. So for your durability testing, it actually goes through a full procedure of what that durability testing recommendation would be, noting that it should typically be done with a scaled down model of the fender, closely resembles the shape, compound, and design of the fender body itself. The minimum number of cycles per the report is 3,000. However, the report does state, or as agreed upon, or as specified, and should be based on dynamic mooring analysis and a project specification. So again, site-specific data, how many times is this fender actually going to be compressed, to what extent, base the testing on that so you actually can test it for the real-world applications. So again, exposed berths, high-frequency berths, or between 2 permanently moored vessels is where this testing would really be desirable to make sure that you're going to get a fender that's going to last under those conditions. Finally, the report also does go through other types of testing for steel fabrication and other steel accessories and things like that, coating as well. So the theme of third-party witnessing is absolutely still present here, in addition to random testing, additional material testing, and things like that. So yeah, it's covered much, much better here. So once we get into chapter 11, I know Sam talked about this a bit, so I'll go into this, go through this one very quickly. Installation and commissioning obviously is going to be very important to ensure that the fender is going to work as it's intended to. Proper installation is going to make sure that the maintenance is reduced, the lifespan is increased to the design, and it's going to be able to operate safely. So fender manufacturers should have a handling, storage, installation, and maintenance manual. It's recommended in the guidelines that will cover considerations for installation, operations, and maintenance of a fender system while it's being installed. It also goes into, as Sam pointed out, with table 11.1, inspection frequencies. The manufacturer's manual should have these. Typically, Trelleborg has 3, 6, and 12-month intervals as a recommendation, and does include all different components of rubber fender systems or foam or pneumatic fender systems as well for those specifics. Most of the time, our recommendations are just visual inspections. It's kind of hard to do in situ mechanical testing, but it is done in some cases for some operators who are interested in that material. Finally, chapter 12, for my portion, sustainability and recycling. So in chapter 12, the report specifically says the fender industry, together with end users, as well as designers and other stakeholders, should take the lead, challenge each other, and cooperate to come to the most sustainable solution for their projects. So basic components of a fender system when you're looking at a rubber fender panel system. Steel and the UHMWPE do have some readily available recycling options. They can both be reprocessed relatively easily with well-established processes and facilities that can already do that kind of work. Typically, Trelleborg doesn't get too much into that because that's more of an operation side, but those facilities do exist readily. Logistics is also in consideration when you're looking at initial carbon impact of these systems. But the biggest challenge typically is the rubber. Again, because it's vulcanized, you've got all this sulfur crosslinks, long polymer chains. It's not really easy to break this stuff down. Current equipment that's set up to be able to recycle vulcanized rubber is all based around tires. So thin cross sections, they're specifically set up to be able to punch out the bead ring and then grind up relatively thin section. Even our small rubber fenders greatly exceed the thickness of some of these tires. So there's not really material or manufacturing or recycling facilities that are able to actually process these properly. So from our perspective, considerations, a little sneak peek of some stuff that'll be coming out hopefully soon, part of the emerging technology from this report. There are options to be able to use more sustainable compounds. So instead of using the SBR, synthetic rubber, there are alternative compounds besides the SDR that can be used. You can use recycled carbon black. That's purely just carbon, so that's easily recyclable. It can come from a variety of different sources. Some of the mixing oils and compounding that build up the compound can also be sourced from more sustainable sources. Most of these, Trelleborg has an eco compound that is kind of in finalization that is shown no impacts, no negative impacts, durability, performance of the compound as well. There's a little bit of an additional cost for it, but truly it is a marginal increase, and it actually is a significant improvement in the sustainability of the fender system itself. So currently, where we're at is most of the time when these are disposed, when you get to the end of life, after the manufacturing is all done, they go to landfills or they get burned for fuel sources. We do have some current developments that I'll get to in a second. Ideally, we're pushing to move towards a fully circular economy to be able to reuse these materials. The first option we have for actual end-of-life fender recycling would be pyrolysis. Whole fender can be inserted into a pyrolysis chamber, and this will heat the fender up. Different components of the fender will be extracted, so the compound will actually be broken down. The energy from the burning of the fender will actually go into repowering some of the energy usage of the facility as well. The oil that comes out of it can be used as an additional fuel source. Carbon black can be used and recycled good as new. And the steel plates can be pulled out to be recycled as steel to start with. So this is something that we've actually validated, and there's a facility that we are able to work with that has been able to start doing some of these pyrolysis recycling for us. The other option that we've got is we're currently undergoing stage 2 trials for actual Fender recycling in WA. Because of the mining applications out there, there's actually a large mining tire recycling facility which has the equipment to be able to handle larger cross sections of rubber bodies. So this material basically gets chopped up in a guillotine, which is what you see here in these pictures, and then it would get crumbed, and that material would then be able to be repurposed into various applications, not fenders, but things like mats, bumper weight plates, things like that. And finally, we do have the ability to reskin foam fenders to restore them to basically as good as new condition. Typically, this is a bit of a challenge out here in Australia because they would be shipped back to our facility in the United States where all of our manufacturing is done for the foam fenders globally. So it's quite a long shipping time, but it is an option if anybody's interested in it. And like I said, they can be returned basically to good as new. So we're going to continue to work on this. Hopefully we'll be able to explore some additional locations for this. Yeah, as of now, it is something that Trelleborg, along with the broader industry, are working on to push for more sustainable options across. I think, yeah, 1 minute over.
Very much spot on.
It's close.
Thank you, James. And yeah, Adam. Yeah, thanks, James and Adam. So before we, I believe the question and answer session, we could move to the panel discussion. That's going to happen now. Before we go on to the next session, which is the panel discussion, I just want to highlight a few things on, you may have seen PIANC has had pretty much one event per month. So we have been running the sessions or events, workshops almost once a month every year. So if you're not a member yet, please jump onto the website and become a member. PIANC accepts both corporate membership and also the individual. And if your employer is a corporate member, so the employees of all that company are automatically the members of PIANC. And for all these events, PIANC generally does a free entry for the university students. And I know here 2 of the students have registered, not too sure if they are present here. But for students, it's a free seminar and workshops. Okay, now the panel discussion. So I'm sure you have a number of questions. So I'll call upon Sam, Harvinder, James, and Adam for the panel session.
Be sharing these 2 between you folks. Cool. Is it on? Yeah, it's on.
So to make the recording possible, I might get the mic around for any questions you may ask.
All right. Do you want one of these for the questions?
Sorry?
I said, do you want one of these for the questions? We can share the one up here.
Yeah, I'll use this and then go around. So you can share 2 mics.
I'm not sure what this is for, but just a question about the new guideline and smaller vessels, the recreational vessels leading into like small ferries, that sort of thing. The guideline historically has been 10,000 tons and above. Does the new one look at that at all? And
I can answer that. The existing working group 33 is better suited for larger vessels. So when you look at a small, for example, tugboat, you tend to see the velocities are very, very high because of the curve of the graph. Now with with working group 211, I think it's going to be a site specific data, but the velocities in the table is more aligned to be lesser than what the working group 33 is. So in other words, 211 is probably better suited guideline for smaller fishing boat or a tugboat.
Yeah.
For the pneumatic fenders, on the performance or energy absorption performance curves, that sort of, I guess, deflection, what is that based? Like, I've heard a few different answers, whether it's just like center line deflection or if it's change. I've even heard like changes of the area of the pneumatic fender. I guess, can you give some guidance on how that deflection is actually measured for that pneumatic fender?
So generally, I guess it depends if you're looking at a vessel that would be compressing the fender uniformly, or kind of like a, say, a round hulled vessel that would be kind of hitting in the middle. It would generally be like the average deflection across the cross section of the fender. So if you have a normal pneumatic fender that would be laid horizontally and a vessel that would come up alongside, it would generally be a pretty even cross section of compression. But if you have a vertical fender, like a hydropneumatic fender, and some type of round hull vessel that would come up along the side, average compression as it goes through would be where you would kind of look at that percentage deflection and get a performance from that.
Right, yeah, because previously I've looked at vessels with quite a severe bow flare, where it's very, like, it's almost like a 45-degree contact surface or something.
Yeah.
So when you say average, what are we averaging here? Like,
yeah, I mean, to be honest, the way that we would typically handle that is we'd plot the vessel, look at the compression and like what the actual compression looks like, and base it off of the area of compression on the fender. So we would model it 2 or 3D and make a determination based on that. So,
right, thanks.
Yeah.
Just a quick question, probably for James or Adam. I suppose looking at your catalog for rubber grades, typically, if we're looking for a higher or potentially a lower energy or reaction, we might want to be going off the chart. So if there's something less than a 0.9 or above a 3.1, what do you actually change? Is it just the carbon black, or you're changing some other things in the manufacture of the fender?
I'll try and answer this, but it's yeah, it's generally the percentage of polymer and carbon black mixture. So the geometry of the fender is the same for each fender height and fender size. That doesn't change. It's just the chemical compound that gets adjusted. The more carbon black, the stiffer it is. So as you move up the rubber grade from 0.9 up to a 3.1, you're adding in a higher percentage of carbon black, to the point where we used to recommend our chemical composition breakdown. We used to recommend 30% carbon black, but we got in trouble with softer rubber grades, where if you put in 30% rubber grade, 30% carbon black, you couldn't achieve a soft rubber grade. And we actually had to do a bunch of sort of technical queries on a project several years ago, explaining that we weren't, compromising on the compound quality. We were just achieving the performance required for that rubber grade.
And that's also a good point, because we can do, just if the situation arises, we can do grades. I think I've seen in some fender sizes, mostly on the cones, down to 0.6, and we can do some intermediate grades as well. So like in between 3 and 3.1, there's kind of a big gap. So like a 3.05 I've also seen before. So even between the 0.9 to 3.1, it's just a tweak of the compound. We just go a little bit further when we get outside of that.
Hey, this one's either for James or Adam, but considering the, I guess, discount or better berthing velocities you get with a monitored berth, have you gone through the exercise of determining, say, if you get, you have your monitored berths system installed on a new wharf, and the cost of that versus, I guess, just going to a conservative larger fender? So say you can drop down to a smaller fender and include the monitor burst, does that come out cheaper than just going for, say, a larger fender?
It's on the to-do list, but no, that certainly will be the case as you get higher up in your fender sizes. I mean, a 15% or a 10% reduction, like in the numbers I presented, is going to potentially drop you down from, say, 1,600 or 1,400, for example. And the change in height of fender is where you're getting your savings. Going from a rubber grade 1 to a rubber grade 2.9, there's a marginal increase in price, but going from a 1,400 to 1,600 is quite large. So I think for the Philips 66 project, I think the cost of that system, which was 6 lasers, a central box and everything, like, was around $150,000 US. And then if you've got 30 fender systems across that wharf at $50,000 each, and you're dropping that down one size, then it can definitely pay for itself. So the short answer is yes, but it depends on the application, and it kind of should be done on a case-by-case basis, and we can always look at that. Well, there's two aspects to that. There's the data for providing a probability or a statistical analysis on your berthing velocity, which reduces your berthing velocity. But then there's also the monitored versus non-monitored aspect. So that reduces it on the monitored situation.
Just one key point on that. The larger the fender, the higher the reaction. Your structure will be left to be dealt with a lot higher. And keeping in mind, a lot of that cone fenders at 30% deflection, you peak your reaction force. So if you're going to jump 1 or 2 sizes bigger, the reaction force can be quite nominal, including factors of safety on your structure.
And that also goes into the fender panel design. When you look at the hull pressure, chains, anchors, every other component is affected by that as well. So if you're able to reduce that reaction with a smaller fender size or a lower grade, it can have a pretty significant effect on the overall cost of the system. Yeah, typically it'll pay for itself.
Just to quantify that a little bit as well, if you're interested, the breakdown of in terms of cost between the rubber cone and all the accessories and steel, rubber is typically 40% of the overall cost of the system, and then the steel and accessories and anchors and everything is 60%. And that can vary depending on the system. For engineered systems like PMFs and pivot fenders, that percentage goes to 20% rubber and 80% steel. So yeah, any reduction in reactions can have a decent reduction in the overall price of the system just through the component design, accessory design, even before you start looking at the structure.
Yeah, just additional point in that case, from my understanding, the reduction in the fender itself, reducing the cost, I guess the majority of the reduction going to happen on the infrastructure itself. And if you compare the pile strength or whatever structure you wanted on the back, I guess that's a huge game changer for the new terminal. But for the existing, you already designed it, so it's going to be just reduction on the maintenance, and development costs.
Do you see any typical for fenders?
Yes. I know, yeah, there's nothing too formal. Trelleborg have a few things where they've designed for maintenance. There's a SISO system, slide in, slide out panel system, which has a replaceable front section. So you can slide out those UHMWP pads in one go, as opposed to changing them out individually, which is on a traditional system. So you would have seen in the photos, or this photo here, you have a number of different pads which are all attached using a stud and hex nut. They'll generally have 9 studs per pad, and each pad can weigh 50 kilos. To change them out, you would potentially need scaffolding, which is quite involved. So the SISO system sort of removes that. I have seen Rio Tinto up in Cape Lambert develop some walkways and access platforms that they can automatically drop down and land on the front of the panel, and access them that way, and even have prefab scaffolding that can be dropped over to access the front of the fender system as well. Some berths have walkways underneath, but again, access, seaward out beyond the cope line can be a challenge. So not standard, a lot of standard systems outside of that CISO system I mentioned. There's been a few custom systems I've seen developed over the years. Anything, you guys? No?
I've got a question, sort of if you frame it up from a perspective of a designer, as we transition from working group 33 to 211, the key takeaway is sort of, I guess, focusing on it as more of a risk-based approach. I guess sort of moving away from prescriptive design, but more, I guess, getting in contact with the operator and getting site-specific data to inform these decisions. How does that risk-based approach interface with ultimate limit state design from a strength perspective, and sort of load factors you'll put on your structural design actions that's imposed from a vendor?
Yeah, I think that's a good question. The Fender itself has got I think the Fender design and factors, the probabilistic factors are used to size the Fender. So that's a whole system by itself. But the reaction that Fender emits into the structure stays the same. So if you use Australian standards, then that same factors are applied on the reaction force. So regardless whether your reaction force is higher or lower, so you still need to go with the same standard. Now, there is some guidance with regards to steel panel. Now, a lot of that usually covers under the steelwork spec under Australian standards, but there's still some guidance in there in terms of minimum thicknesses for durability requirement. So that's the only interface we've got from 211 to structural design. But with regards to your question, it's the same. You don't see any change in that.
Okay, I guess sort of where my mind then goes is in 4997, for example, when it's a normal berthing event, there's a 1.5 load factor, and then it specifies use a 1.0 load factor on an abnormal berthing event. So when you then actually look at a fender and trying to think of what event would cause a fender to put 50% extra reaction load on your structure, that's kind of where it breaks down in my mind a little bit with.
Correct. No, that's good. That's a good question. I think now fenders rubber is a material. If you don't compress it, it hardens up over time. So now it's similar to a car tire. If you don't drive it and then you take your car after 3 years, although you've got new tires, you're going to skid on the road because the rubber is hardened up. It's just materials. So for marine fender, if it's left untouched for 3 months, what we have found is you get a peak of at least 10%, 5 to 10% additional reaction force when a vessel is to come and impact on it. That's why a fender needs to be compressed every now and then. Otherwise, you end up getting it harder. So all these factors of safety in structural design needs to cater for that shortfalls of this fendering system, and that's where I encourage stick on to 1.5. If you're looking into structural design.
Yes, to add to that, that's a great question. From my understanding, there are 2 components you have to see it separately. Design of the fender itself, that is a risk-based approach, and WG211 is addressing that one. But once you realize and finalize the load, that's going to be additional load on a superstructure, on a piles or whatever structure you are designing. Then you go with the AS49, 97, AS4100 whatsoever. You have to consider all of the factors that you want. So there are 2 different, I guess, aspects of the design. For the fender itself, you're selecting the fender, the design of the fender, what the size is going to be. Once you finalize that one, then you need to go to all of the dead load and live load standards and apply all of the loading factors. So that risk-based design is not impacting the design of the piles or the infrastructure behind of the fender.
Okay, thanks.
I have a question for Adam on the fender panels. You mentioned 20 years. That seems to be in line with the fender, not with the structure behind. Is that common?
For the panels themselves? Yes. Yeah. So a lot of times the panels are going to be governed by the coating specification. So ISO 12944 for the highest durability class, I believe, has a 20-year design life. So in theory, the steel is designed for like a, infinite limit state. So it's based on the structural code. So really the design life consideration is going to be coating failure and corrosion, where you lose that section loss and end up with failure in that mode. So yeah, that's what it's driven by. It coincides with the rubber expected design life for the actual rubber fender itself. Conveniently, I guess. I don't know if that's intentional or not, but
But you're saying that after 20 years, the paint could be repainted and reused typically?
If the coating is maintained properly to where any minor incidents of chips or any little damages would be covered up, touched up to where you wouldn't actually get corrosion starting on the steel. You wouldn't have any section loss of the steel itself. Then in theory, yeah, absolutely. You could, you'd be able to blast and recoat the panel and get another 20 years of design life out of it. So.
Okay, thank you.
I was working on a project with, I think, Matthew from Trelleborg last year, and he had mentioned that in the new working group that it affects the fender panel sizing. I hadn't actually drilled down to that part yet and seen how that plays out, but can you give us a bit more information on how that plays out?
Yeah, so it has to do with the load factor. So in the working group, I forget the exact name of it, but one of the load factors essentially has to be applied to the hull pressure calculation. So similar to as Harvinder mentioned, it's a 1.3 to 1.5 load factor that is applied to the force in the hull pressure calculation. So 33 did not have that. It was just design reaction force over area. Now that we have this additional load factor, you have an additional 30 to 50% load that's applied when you calculate that. So it is something to consider when you're looking at that panel sizing. So
the hull pressures have gone up there as well.
Yeah.
On the 211. So
yeah,
balances out a little bit. Because typically we'd always see 200 kPa, just
Right.
consistently across the board. Hull pressures on.
Yeah. Yeah, and there's a lot better clarity in the hull pressure section around line load contacts and the actual hull structures to detail a bit more how the hulls are actually built, and that a lot of the hull can actually handle much higher hull pressure than that average. And that average hull pressure is basically a simplified way to not have to go through and do a high level detail analysis of hull structure and capability and loading capacities and all that kind of stuff. So it goes pretty well through the areas in the hull, like the deck structures and the intermediate decks can actually handle much higher loading. But in order to simplify it, so we don't have to go through that detail analysis, which a lot of times isn't really available, you can just use that average hull pressure for design. So.
Yeah, perhaps quick questions for Harvinder on the hull pressure in WG211. There seems to be no hull pressures for Navy vessels. Has there been sort of an action to try and obtain them?
That's deliberately left out because every country has got different Navy requirements, and very often information like that is quite classified. So it project specific if you're on Navy, any Navy projects.
Okay, thanks.
I can fill in one. So this is for James and Adam. It's a smart dash system where it gets the velocities, angle of point of contact on the fenders, etc. So since this WG211 was released, were there any increase in the sales in terms of that smart DAS, so that this could be reliably used for the Fender design to have not the largest size, which otherwise using W33. You get this, yeah.
It's technically not my area. It's Chris's area here, but yeah.
G'day, my name's Chris. I do docking and mooring, so this is super exciting for me. Listen to Fenders. Yeah, Smart DAS, we are seeing an increased inquiry amount. And also, what was you asked the question about cost balance. We also find that there's a benefit from operators to get a history of what's happening during the berthing. So it's not just related to this topic of conversation. It's also to ongoing operational benefits and understanding how your berth is performing. But yeah, there is an increased inquiry amount at the moment. Also for loading on the actual berth, larger vessels, increasing the capacity of your berths and your operation. So lots of different things that it can offer.
Following up on that, say you're designing like a smaller remote structure and you don't want to put one of these systems in long term. Would you guys hire them out for a period of time to collect data like you would for any other sort of data collection?
Yep. Well, at the moment, we're still building that. It's new. We've had that inquiry come up new as well. So we haven't got a particular model, but yes, it's something that we're looking into. The lasers we'd still like to have installed, cast in, but they're only small piece of things, so it's not too hard. And then we've got a box. We're looking at putting a battery pack on it and then using it as a temporary hire out. That kind of stuff. Yeah, absolutely.
When you refer to it as hazardous,
so docking aid systems have been generally used quite prevalently in the LPG industry. So hazardous areas, basically potentially explosive environment. So the equipment has to be electrically protected, either by intrinsically safe or actual housing that contains explosions. So the lasers most likely still be those ones. They're a bit more expensive, but fairly robust. It's the control panel, the smarts, which we can place at different positions on your infrastructure outside hazardous areas to suit or wherever it's best placed so you can not damage it. It works. So,
Your voice is okay, but I just want to.
Okay.
In case.
I got
Yeah, I've just got a further question on the kind of the basis of Working Group 211, which really seems to leverage around getting good site data and engagement with operators, port operators, tug operators. What I see kind of in my experience is that is really difficult. That isn't forthcoming, even with very large players on global size ports. They either aren't mature in that space of data collection, or they don't see the need for, let's say, the short-term capital piece of a Fender replacement project. So I can kind of see some challenges there of, at the moment, the clients that I'm dealing with don't see the value in getting that data in the long term. Maybe if there's some kind of rental scheme that could be done for a period of time if you've got forthcoming understanding of your capital delivery of replacements. Do you see that changing, and how do you see that changing? Because I'm just not sure I see those links with, let's say, Working Group 211, and that being the key to changing that mindset of data collection for vessel motions.
That's a can of worms. Yes, you're right. Now we're moving from a very deterministic approach to a probabilistic approach. I think the selling point here is we're giving you more accurate design, more optimized, more pinpoint, more bespoke design. Now, to get there, we need data. We can't pluck data from the sky and just put it in just because you're located in a geographical area. I think asset owners need to appreciate the fact that there's a shift in the way we design things. It's not only fenders, but there's a lot of structural design in the Euro codes and all the sort of codes which are moving towards probabilistic rather than a deterministic approach. I think we need to. I think it's our duty to make port authorities aware that this is very, very important moving forward in terms of new development or upgrades or existing asset management. So, yes, it's a work in progress. It is a challenge. I do see a lot of positive changes in the European continent. There's a lot of awareness of green ports, sustainability, data collection, automation. But I think that needs to move across to where we are here, and it needs to be a sort of the awareness needs to be in industry with this sort of data. So yes, I would think you probably need to go and speak to your clients again and perhaps try to convince them if you have the chance.
Yeah, just to add to that. So I think, this is still a pretty new specification, and this concept of having this much reliance on the site-specific data is still pretty new. This guideline's not even really in effect for another, I don't know, however many months. So I think it's our responsibility to educate and drive that kind of thought process in the industry. Of course, people aren't going to have that kind of information now, but hopefully as it becomes more prevalent, as consultants are able to work on projects where they can kind of directly compare with site-specific data, and if we didn't have site-specific data, to actually have more examples of how it can be optimized, the cost savings that can come with that optimization, I think it makes a really easy case for end users to invest that relatively minor upfront cost to be able to then have a lot of benefit in the optimization and design. If you know you're going to do a project in 3 years, invest a year of getting that data, and you can save a significant amount as you get towards that design in a couple of years. So yeah, I think it's going to take time, but I'm hopeful that we'll be able to trend in that direction.
Just following on from that a little bit, Sam, if you can take your PIANC hat off for a moment and just leave your asset manager's hat on. Do you want the responsibility of telling us designers the relevant criteria we should be using for your port for the next 50 years? It's this whole reliability part is quite different to everything in the past, where it's always black and white. Now you as your asset owner are setting up the trend for us to be able, us as designers, to not so much have our ass on the line, so to speak.
Well, that's pretty, I guess, difficult question to answer, because when you're talking about, port operators and asset owners, they are sometimes not, they don't have a simple structure. They have an investor, they have, the insurance are, involved, and also you have the operator and also the other stakeholder who are, exporting or importing products. Okay, so everybody get involved, and you want to just tell them, because whatever development in the design or change of standards or guidelines, it's gonna vary some costs. And somebody, from the decision makers, asset owners, budget owners, they need to make a decision. So they simply gonna ask the questions, okay, how we are going to, for the existing one 40, 50 years ago, as a designer, you want to jump in and say, okay, how we are going to implement and adopt the new guidelines into the asset, that we already have, and what's the impact going to be. So it's not an easy answer, and this is what I started probably a year ago, And the first question I was asked, okay, what's the benefit going to be? Do we have any risk in terms of, underestimating the fenders, or we have, once, I did the calculations, okay, probably our fenders are overestimated. So they say, okay, well, what's the risk? So my next probably challenge was that, okay, if we are reducing the fender size, because nobody has seen that one, you are reducing the hull pressure as well. So it's going to be impact on the ship owners or the liners. Then the point is that, okay, do we need to be worried about the ship owner because they have other safety factors when they design the hull and all of the superstructure of the vessels? So probably if you go to the history, how many vessels being damaged because of the inappropriate fender, probably we don't have much information in the history. But I can tell you, we have a key line truss between our fenders and mooring structures. And I can tell you how many times the ship liners, they damage our key line trusses. And, it has been, but nobody has considered, none of our wharves going to withstand against the force of the vessel impact. It's like if you, look at was it Baltimore Bridge that was impacted and, just collapsed like, a domino because nobody designed it. And the force is huge. You have to prevent that sort of, collision. So these kind of, I guess, questions, when you are inside of the operators, you're going to get asked, and it's different with the, position when you are in the design, consultant engineer, you try to design it from the scratch and you go with the standards, you have the flexibility, you do everything. But when the system is in operation and it is live, that's going to be difficult to address. But my point is that, the measurement and collection of data, no matter going to be fender or the mooring or other environmental stuff, is a key game changer for the future development. That's, what we started to collect, collate data, integrate, put it in the system, whether we are going to use it for the, the fender or the mooring or the, the other asset that we have. The climate change is one of the factors that we are considering. Even, we consider the environment and collecting the data and we are just, installing, assume that, some smart technology, but the question going to be, what's going to happen within 20, 30 years that we already know that within climate change, the wave condition, the tidal condition, the sea level rise going to change. How that we are going to add additional factor if you are considering the design life more than 30 years, 50 years. And this is part of the sustainability that, been addressed within WG211. Have I answered your questions or? Yeah.
Sorry, but I can't help it just to add to Sam's point. I think you quantify it by risk, the short answer of it. I'll give you an example. You go to a car showroom, you buy a new car. Someone asks you, do you need lane departure warning? I don't need it. I'm a very careful driver. But it, again, to put it in a risk perspective, you put it on your car just to warn you, just in case that one or two times that you feel that you need to use it. So the same thing applies here. A port owner needs to de-risk themselves. And this is probably one of the measures they have to sort of take it. Because it gives you, it gives you low fender, but it gives you a sense of monitoring and protecting your berth as well. So there's a lot of usage for that data that you collect. I mean, if more an insurance company comes to a port and say, all right, I'm not going to pay for your damage in there, you pull out your data and you said, hang on, XYZ came in and they came over the speed limit, and that's probably why we have to target our claims to. So there's a whole big picture at the back of it, which I think needs to be appreciated when we talk about data collection.
Yeah.
Yeah, quick question, Sam, for you. As the asset owner, DBCT, I think do they do berthing velocity measurement there?
Yes, we do that. Yeah,
Yeah.
yeah. It is not only for that one. We also have, the mooring force cells as well, because we consider the fender and the forces and the mooring reactions at the same time, because it's going to impact both of them. And in some cases, because we have exposed to swell with more than 9-10 seconds, and that's going to impact hugely the snapback issue that we are managing. And we have a very sophisticated risk-based snapback program. It is like a live, and we have a very large billboards with the live data, and we collect all of the data, analyze at the same time, just send the information to the wharf area and the shipping officer. So we measure all of these information for the whole management of the wharfs, fenders, moorings, and also managing the mooring lines.
You also have DMA sort of behind your mooring, or is it just practical measurement? Like
What do you mean by DMA?
Dynamic mooring analysis behind sort of your.
We don't do that online, because the point is that that was a discussion a few years ago. The loading cell that we have and the PLC that the data transfers to it, it has a 4-5 second lag. And this is, I guess we had that discussion with a lot of, manufacturer to reduce that time lag. The point is that we have a threshold for every hook that we have, and that threshold, being set up based on the maximum of 20 ton based on every hook. And in some of the, quick release hook, we have 8 hooks. So when it goes above 20, it become red. And then in some cases, we just send a warning. But the point is that the time needed for the information to transfer to PLC, and then the reaction that's being taken automatically or by officers sending back to offshore, it's going to take 10-15 seconds, and it's too late. So what we are going to do, we are measuring the environment, the size of the vessel, and the trends. And also we analyze 5 years past data, and that's going to happen every time. So we get to the 5 years data, analyze, create some category in terms of low, moderate, and high risk. So if the sea environment goes to the moderate, just certain trained people they can access, which understand what's going on, and they can make a decision quickly. The normal maintenance team and the other crew, they are not allowed to get to the area. So it's a very sophisticated management system. We are trying to enhance it. We also discussed whether, because that was the discussion, whether the online dynamic mooring analyzer is gonna beneficial. Because of that time lag, we haven't got to a certain answer to implement it. It's not matter of the cost, it's matter of the, I guess, efficacy of the program into online mooring management system.
Yeah, okay, thanks, Sam. One last question then. That the 195 millimeters a second design of berthing velocity, how does that measure up with the measured data that you have available now? That conservative, or is
it's very difficult to say it, because you have to consider the inaccuracy of the measurement as well. If you want to see the spikes, in some cases it goes over. That's what I can see it in the data. But the other point is that we have some incidents when the tug couldn't follow the instruction, because of the sea environment. In some of the cases, I do remember, I was just reading that report that, ended up to one of the incidents reported. The vessel was alongside of the wharf, and the loading was complete. So two tugs approached the large vessel, one from aft and one from the foreside. So the way is that they should parallelly, based on the instruction, they should get offset in parallel to the wharf alignment. But the foreside tug start pulling the forces, the back side couldn't maintain the force, so it was like swaying in one angle. And what happened, the aft of the vessel just came between the fender system and hit the keyline truss and buckled heavily the keyline truss. When we saw the environmental condition, everything was calm. So there wasn't any high wind, there wasn't high swell, there wasn't even, sea waves. So it was lack of maintaining the tension. So the point is that velocity, that was the sailing out velocity, and we have the same issue when they are tensioning the mooring lines, because they are getting close to the wharf. It's very large vessel, and the tugs are bringing the mooring line. The shipping officer, they are taking the mooring lines and starting to coil the mooring around the system. The tension sometimes is not maintained at the same time, and that's speed the vessel towards the fender before making it just intact with the whole system.
Thank you.
Any other questions? Maybe another one for you, James and Adam. What sort of cost balance do you have from the manufacturing of the fender units to the testing of it? Because the current WG211 is more elaborate on the testing requirements compared to the previous one. So is there any a borderline to say this many, any number of fenders more than this would be cost effective, but lesser than this is maybe testing would cost more?
I think this, Adam, I'm sure you'll be able to add to this, but there's different levels of testing, and testing is relatively inexpensive for material chemical composition testing. It's taking samples of the rubber before and after vulcanization and molding, producing lab tests either in the factory or at a university or a third-party independent lab. All that's very inexpensive. There's not a lot of extra handling of material. And for the benefit you get for having that in your specification and knowing that you're getting what you've specified, it's a no-brainer. If you've got $100,000 worth of fenders or a couple $1 million worth of fenders, we're talking thousands of dollars to do some extra testing, maybe $5,000 across a full project. When you start to move into performance testing and full durability testing, everything like that, that gets more and more expensive every unit. So actually, I got a question. Performance testing and then the percentage recommendation in working group 211, is it still 10% or is it? Yeah, okay, great. Probably should know that. But anyway, that's good to know. So we'll always follow 211, regardless of whether it's specified. We will always specify 10% of the fenders that have been ordered, regardless of the order. Depending on the project and I guess the risk profile, that percentage can increase. And there is a bit more of a cost to that because you have to take the time and the labor to put that into the test press, test it, wait, make sure it normalizes, do the full process. Same goes for break-in, deflection as well. While very important, you then have to put every fender in. And if you've got a continuous key wall, that might be 30 fenders. So there is a cost and a time element to doing that. I think it depends on the risk and it depends on the size of the project. So a continuous key wall project with 30 fenders, 40 fenders, 100% performance testing might be a little bit cost prohibitive, depends on risk. For a terminal where you've got 4 breasting dolphins and 4 fenders, I definitely recommend 100% performance testing. Then you actually have the accurate data for each fender as well, which you can then continue to have in your records.
Yep. So yeah, like James said, the simple TGA physical chemical testing kind of stuff is going to be very inexpensive relative to the cost of a fender, even if you have a pretty small quantity of fenders. The most expensive thing would be like third-party independent testing, actual performance of the testing for the performance testing. Or if you get into correction factor verification, that kind of stuff, because then you run into, with the correction factors, a lot of different tests. And with the third-party performance of the performance testing, there's only, like I mentioned, a handful of laboratories in the world that can do that. So you'd be sending basically the fenders from manufacturing to South Korea to do that testing, or to Washington State, probably from Australia, and then shipping them to the final location. So that would be a much more time and cost intensive test. If it's a really critical application, you need that level of security to manage the risk, then it's definitely an option, but that would be much more expensive. It's way easier to do when we were in the States because there was one on each coast, and you just pull one off after delivery and send it up there. It's easy to do, but a little bit more difficult here in Australia. So
you said correction factor test. Have you had that request before from any of the clients?
No, so that's a new thing in 211 is the optional test, project specific, for verification of the correction factors. I don't expect that that's going to be a frequent request. To be honest, I was surprised when I saw it in there as well. But for some manufacturers, if you want that verification to be able to be assured that the correction factors they're using are accurate, it could be useful. But again, it would be scale model testing. It wouldn't be on a full size fender. So there would be, some optimization there. But
so if it is done on the full scale model, would that be a CV, constant velocity, or the actual?
It depends on the test. So for the temperature and angular, that would be a CV test. For your velocity factor, inherently that is going to be a decreasing velocity test. So that would be one that would, start out quick and slow down. So, yeah.
Yep. Thank you. Any more questions? Maybe time for the food. Is that okay if we wrap it up?
I'm good if you
We
are.
have like 8 more minutes. All right. If there are no more questions, I thank the panel discussion members and also great participation from the attendees. Thank you very much. And let's have the food. Before we go on to the food, I would like to once again thank Jacobs and Trelleborg for sponsoring this event, and also the Engineers Australia for providing this facility and the equipment. And thank you all for attending this. Hope you have a good event, technical event, and the networking event follows on. Thank you once again. Sorry, you have anything to say, Adam?
I was just going to say thanks for doing a lot of the heavy lifting on the organizing, Harry.
Yeah.
So
No worries. Yeah, all good. Yeah, thanks.